Russia is secretly testing a colossal new war machine unlike anything the world has ever seen. This next-gen beast is designed to break the sound barrier and rival America's top stealth technology, which is rumored to redefine air warfare forever. With leaked footage sparking global alarm and military analysts scrambling for answers, Russia isn't just testing this jet, it's sending a warning. Could this be the beginning of a new arms race? Is the world ready for what Russia is about to unleash? Join us as we reveal the terrifying details of Russia's $13 billion supersonic fighter jet. In 1979, the Soviet Union started planning for a new type of fighter jet that would enter service in the 1990s. This I-90 project aimed to create a multi-role aircraft with strong ground attack abilities, replacing older jets like the MiG-29 and Su-27. After the Soviet Union collapsed, money became tight. So in 1999, the Russian Defense Ministry launched a new project called PAKFA, also known as I-21. A competition began in 2001, and by 2002, Sukhoi was chosen to lead the project. This effort led to the creation of the Su-57. The Su-57 is Russia's first stealth fighter and belongs to the fifth generation of fighter jets. While designing this fighter, Sukhoi considered the American F-22 a starting point, but made changes to improve it. They felt the F-22 couldn't do everything needed, like carrying a wide range of weapons or handling specific flight problems if the thrust vectoring system failed. Sukhoi aimed to build something more flexible and better suited for multiple roles. The jet has a sleek shape, a vast body, and two engines spaced far apart. It has movable wings and tail surfaces to help it stay agile. The wings are shaped like a trapezoid and include several movable parts for control. The Su-57 also uses thrust vectoring, changing the direction of engine thrust, to improve how it flies, especially during sharp moves or stalls. Special surfaces on the wings help control airflow and improve performance at steep angles. To slow down in flight, the Su-57 uses a mix of control surfaces that move in opposite directions to create drag. The plane is made from a blend of strong materials, mostly aluminum and titanium, and many lightweight composite materials. These composites cover most of the jet's surface and help reduce weight while keeping the plane strong and stealthy. One of the Su-57's key strengths is the ability to carry a wide range of large weapons inside its body. These weapons are stored in two central bays beneath the aircraft between the engines, and two smaller side bays near the wings. Keeping the guns inside helps the jet fly faster and more smoothly while maintaining its stealth features. The jet's design allows it to be very agile. It has a naturally unstable structure, on purpose, which is controlled by an advanced flight system called KSU-50. This system and engines that can change direction mid-flight make the Su-57 capable of complex and extreme maneuvers like Pugachev's Cobra and the bell turn. It can even spin flatly in the air without dropping much altitude. The Su-57 can reach speeds up to Mach 2 thanks to powerful engines and innovative aerodynamics. Even more impressively, it can fly at Mach 1.3 without needing afterburners, a feature called supercruise. This allows it to strike targets farther away, faster, and with less fuel. With a large fuel tank, the Su-57 can fly over 1,500 kilometers at supersonic speed, more than double the range of older jets like the Su-27. It also has a refueling probe that extends during flight to increase its range even further. As Russia's first stealth fighter, the Su-57 uses many tricks to stay hidden from radar. Like the American F-22, it's shaped in a way that bounces radar waves away from the source. The edges of its wings, control surfaces, and panels are angled carefully to reduce visibility. The jet's weapons are hidden inside, and antennas are set below the surface to keep the sleek look. Special coatings on the body help absorb radar waves, making the plane even more challenging to detect. The Su-57 also uses stealth techniques in its sensors and air intake design. Its infrared sensor, which helps it spot enemy heat signatures, faces backwards when not in use and is covered with radar-absorbing material to stay hidden. To reduce radar reflection from the front of the engines, a common weak spot in stealth aircraft, the jet uses curved air intakes lined with radar-absorbing material. These curves hide the engine blades from radar. Any part still exposed is blocked by a special grid. much like what's used in the FA-18 Super Hornet. Even the cockpit canopy is designed for stealth. It's coated with thin metal oxide layers that absorb radar waves, reducing the cockpit's radar visibility by 30%. This coating also protects the pilot from UV rays and heat. To boost its stealth even further, the Su-57 is built with much tighter tolerances than older Russian jets, meaning its surfaces fit together more smoothly to reduce radar reflections. The Su-57's current propulsion system, the AL-41 Phone engines, delivers powerful thrust and advanced maneuverability, especially when paired with its thrust vectoring nozzles. These engines are a significant upgrade over previous Russian power plants, offering around 14.5 tons of thrust in afterburner and up to 15 tons in emergency mode. Full Authority Digital Engine Control integrates these engines directly with the flight control system, allowing smoother transitions, greater stability, and precision handling during extreme maneuvers. The engine inlets are also smartly designed for both high-speed flight and rugged operations. Variable ramps adjust airflow during supersonic flight, while retractable mesh screens protect the engines from debris, which is especially useful when operating from improvised or damaged airstrips. However, Russia is still developing a next-generation engine, the AL-51F1, also known as Izdeliye-30. This engine, expected to become standard with the Su-57M variant, will produce more thrust, up to 17 tons with afterburner, improve fuel efficiency, cut costs, and enhance stealth using composite inlet guide vanes and a specially designed nozzle. A key feature under development is the flat nozzle, which reduces the jet's infrared and radar signature from behind, one of the Su-57's current weaknesses. This new nozzle began flight testing in late 2024 and is designed to integrate with the current airframe with minimal modification. The Su-57 has an internal weapons configuration to preserve its stealth profile during combat operations. It features two tandem central internal weapon bays, each approximately 4.4 meters long and 0.9 meters wide, capable of carrying a variety of heavy munitions. In addition, the aircraft has two smaller side weapon bays located near the wing roots, which are designed for quick-launch, short-range missiles. These bays are equipped with specialized launchers. The Vimpel UVKU-50L, used for rockets weighing up to 300 kg, the UVKU-50U for ordnance up to 700 kg, and the VPU-50 launch rails, which are used in the side bays for lighter weapons. For air-to-air combat, the Su-57 carries a mix of medium and short-range missiles internally. The central bays can house up to 4 beyond visual range K-77M missiles, which are upgraded versions of the R-77. These feature an active electronically scanned array radar seeker, a dual-pulse motor for extended range, and redesigned aerodynamic surfaces. The side bays carry 2 R-74M2 short-range infrared-guided missiles, which have been specifically modified with a reduced radar cross-section to allow internal carriage. Russia is also developing a new rocket, the KMD, as a next-generation replacement for the R-74M2, with expected agility and sensor fusion improvements. Regarding long-range engagements, the Su-57 is compatible with the Izdeliye-810 missile, a more compact development of the R-37M long-range air-to-air missile. This missile has redesigned control surfaces and an updated propulsion system, allowing it to be carried internally, 2 per bay. The standard R-37M can still be carried externally when stealth is not a priority. For air-to-ground missions, the Su-57 can carry several types of precision-guided munitions. These include the KAB-250 and KAB-500 bombs, weighing 200 and 500 kilograms, respectively, which are designed for precision strikes. The aircraft also supports a diverse missile loadout, including the Kar-38M tactical missile, the Ka-35U anti-ship missile, the Ka-58 UHK anti-radiation missile for suppression of enemy air defenses, and the Kar-69 cruise missile, formerly known as the Kar-59 Mk2, which is optimized for stealthy standoff attacks. Additionally, a new hypersonic missile is under development for the Su-57. This missile is reportedly similar in performance to the Kh-47 M2 Kinjal. Still, it is being designed with smaller dimensions and intra-body integration to allow internal carriage within the Su-57's central weapon bays, further enhancing its stealth capabilities. The aircraft is also armed with an internally mounted 30mm 901-4071K autocannon, a modified version of the GSH-39-1. This gun is located near the right leading-edge vortex controller and carries 150 rounds. It has an effective range of approximately 800 meters against aerial targets and up to 1,800 meters against surface targets, making it a versatile weapon for dogfighting and ground attack missions. On 25th of December 2020, the Russian Defense Ministry announced that the Su-57 had officially entered service with the Russian Air Force following the delivery of the first production aircraft. This initial aircraft was assigned to an aviation regiment in the Southern Military District, based in Lipetsk. The early production batch was designated primarily for military evaluation, operational tactics development, crew training, and conversion to the new platform. The first operational combat unit to be fully equipped with the Su-57 is the 23rd Guards Fighter Aviation Regiment in Jomgi within the Eastern Military District. Deliveries to this unit began in 2023, with the regiment's proximity to the Komsomolsk-on-Amur aircraft plant offering logistical advantages for support and integration of the new aircraft. Russia has stated that a complete regiment of 24 Su-57s will be operational by 2025. The Su-57 has reportedly seen combat service during the ongoing conflict in Ukraine. On 19 October 2021, Russian Army General Sergei Surovikin, then commander of all Russian forces involved in the war, claimed that the Su-57 had been deployed in both air-to-air and air-to-ground roles and had achieved kills in both. According to unverified Russian reports, the aircraft shot down a Ukrainian Su-27 using a long-range R-37 missile. However, independent verification remains lacking despite these assertions, and no conclusive evidence has emerged to confirm combat kills. Several Su-57s remain stationed at Lipetsk and Akhtubinsk air bases, primarily involved in development and trials. Satellite imagery from December 2022 confirmed the presence of 5 Su-57s at Akhtubinsk Air Base, located approximately 500 kilometers from the Ukrainian border. In May 2024, Ukrainian sources reported an uptick in Russian Su-57 sorties targeting Ukrainian territory. These airstrikes were reportedly launched from Russian-controlled airspace over Kursk, Bryansk, and the occupied region of Luhansk. The strikes employed the latest Ki-69 stealth cruise missiles, highlighting the growing operational role of the Su-57 in long-range precision strike missions from standoff distances. While other countries are still trying to stop the Su-57, Russia has moved ahead with something new. In 2021, Russia showed off a non-flying model of the Su-75 Checkmate fighter jet at the Max Air Show, with President Vladimir Putin attending. This jet was first supposed to fly in 2023, but that was pushed to 2024 and now to 2025. If things go as planned, deliveries might begin in 2026 or 2027. The Checkmate is meant to be affordable and aimed at countries looking for a cheaper fighter jet. It's built to compete with planes like the US F-35 and China's FC-31. Russia hopes to make around 300 aircraft over the next 15 years. Each plane is expected to cost between $25 and $30 million. As for design, the Su-75 includes features that help it avoid radar, like a special air intake and hidden weapon storage. Its large wings suggest it's built to fly high, possibly above 40,000 feet. The Checkmate's unique air intake design wraps around the lower nose and follows a more straightforward style called the diverterless Supersonic inlet. This design, which was first seen on the Boeing X-32, helps cut costs and weight compared to older, more complex systems used in jets like the F-15 or Su-27. Instead of a regular tail, the Su-75 uses a V-shaped tail similar to the one found on the Northrop YF-23. This V-tail uses a combined control surface called rudder vaders that handles up, down, and side-to-side movements. However, because these are more complex to control, the jet needs a more innovative flight control system to manage them. The Checkmate is expected to fly up to 3,000 kilometers without refueling, carry about 7,400 kilograms of weapons, and hit speeds close to Mach 2. It will have an internal bay with 5 missiles and a gun, keeping weapons hidden to reduce radar visibility. In 2023, patent documents showed that the jet's body was updated. Changes to the sides, air intakes, and other parts were made to help it stay off radar. The updated shape also seems to give the jet more lift. The engine will likely be the Saturn Izdeliye 30, the same one planned for the upgraded Su-57. This engine is lighter, more efficient, and has more vigorous thrust than older models. It also promises a longer working life, which could make maintenance easier over time. Though no photos were allowed inside the cockpit, a journalist who saw it described it as very similar to the Su-57. It features a modern glass cockpit with 2 large LCD screens and a wide-angle head-up display that helps the pilot keep track of critical flight information while staying focused on flying. The Checkmate's electronics are built on an open system, which means upgrades and fixes can be made more easily. It also uses an onboard diagnostic setup called Matryoshka that helps detect problems without needing external tools. To keep costs low, a new affordable ESA radar is in the works, and many of the jet's parts and systems will be shared with the Su-57, according to government officials. This approach helps cut development time and spending. Russia isn't stopping with the Checkmate. Work is moving fast on the MiG-41, a 6th-generation fighter meant to take over from the older but mighty MiG-31. This new jet aims to push into high altitude and even near space flight. That's right, Russia plans for the MiG-41 to fly at the edge of space. The MiG-31, known as the Foxhound, could reach speeds near Mach 2.8 and carry massive long-range missiles like the R-37. The new MiG-41 will aim to be even faster and wiser. All its weapons will be hidden inside to reduce radar visibility. Russian sources even claim the jet will include technology never seen before in any fighter. Known as the PAKDP program, this project is focused on creating a super-fast, stealthy, high-flying interceptor. The goal is to launch it sometime in the 1930s. The design was reportedly completed in late 2019. MiG's top boss, Ilya Tarasenko, confirmed in 2020 that the MiG-41 will be a new jet built from scratch, not just an upgrade of the MiG-31. It's expected to fly at speeds beyond Mach 4, feature a laser system to shoot down missiles, and be capable of flying extremely high, possibly between the tropopause and the edge of space. The MiG-41 is set to build on the MiG-31M's technology with an advanced Zaslon M radar for improved tracking and targeting. It might also use a version of the Izdeliye 30 engine currently being developed for the Su-57. The R-579-300 engine is another option that could work well for this fighter. One of the biggest challenges for the MiG-41 is the pulse detonation engine. This powerful engine must handle extreme forces, making its durability and maintenance a key issue. The PAKDP will also incorporate stealth tech to stay undetected by enemy radar. An exciting addition to the MiG-41 is Russia's development of an electromagnetic pulse gun. This could revolutionize aerial combat, allowing the aircraft to turn off targets at greater distances. Russia is aiming to equip the MiG-41 with an EMP cannon by 2025, with a less powerful version possibly used for taking down drones. The MiG-41 might also carry the powerful R-37M missiles. In the future, the MiG-41 could even have an unmanned version. Suppose the MiG-41 makes its first flight by 2025. In that case, analysts expect it to be fully operational by the early 2030, rather than the original target of 2023. Apart from its latest fighter jets, Russia is also working on bringing back an old project with a fresh purpose: the Okhotnik, a large unmanned combat drone. Work on the Okhotnik began around 2011, when Sukhoi was chosen to lead the development of a new heavy drone that could handle both spying and attack missions. This drone is a joint effort between Sukhoi and MiG, using earlier research from the McCoy and Scott project. The aircraft is being built by the Novosibirsk aircraft plant, which is part of Sukhoi. In September 2019, Russia released a video of the Okhotnik flying with the Su-57. The drone flew independently for over 30 minutes, working closely with the fighter jet. This test showed how the Okhotnik could help extend the Su-57's radar and allow it to fire long-range weapons from safer distances, far from enemy defenses. By early 2021, Russia had begun building 3 more Okhotnik prototypes. The second model was slightly improved from the first, while the third and fourth were made to match what the final production version would look like. These newer versions featured better onboard electronics and changes to the drone's structure. One big improvement was a flat engine nozzle, which helps reduce the drone's heat signature and makes it harder to detect. In February 2021, it was reported that future Russian warships, specifically the Ivan Rogov-class amphibious assault ships, could carry up to 4 Okhotnik drones for spying and attack missions. The Okhotnik has a flying wing design with no tail and a smooth shape to reduce how easily it can be seen by radar. It's made using special materials and coatings to help it stay hidden while flying. The drone weighs about 20 tons and has a wingspan of 20 meters. It's powered by either the AL-31F engine used in older Russian fighters or a newer version called the AL-41F. Its top speed is said to be around 1,000 kilometers per hour, and it carries its weapons inside the body to stay stealthy. This aircraft can carry up to 2,000 kilograms of bombs and missiles inside 2 internal weapon bays. This includes both freefall bombs and guided weapons. With these advanced jets, Russia isn't just securing control of its skies, it's gearing up to strike deep into enemy territory and unleash total chaos on its rivals. The United States Air Force has always had their technological needs catered for by 3 of the biggest aerial combat vehicle manufacturers in the country: Northrop Grumman, Boeing, and Lockheed Martin. However, the advent of Elon Musk's SpaceX in 2002 birthed the rise of serious competition in the creation of aerial vehicles. Fast forward to 2025, and SpaceX has reportedly come up with an enticing new bomber plane for the United States Air Force. Could this be the future of bomber jets? Is there a chance that this new cutting-edge bomber sparks a global arms race? Join us as we discuss the brewing bomber between SpaceX and the United States Air Force. Although top high-tech companies like Lockheed Martin, whose Skunk division has played a major role in the creation of some of the United States' greatest combat aerial vehicles, and Northrop Grumman have been at the top end of the pile as the go-to for the America's Department of Defense, the sudden surge of Elon Musk and his SpaceX company has finally brought the heat, the competition needed to give the United States their best. While SpaceX's affiliation with the government might seem sudden, it didn't start that way. It all began with a man who dared to dream, to challenge the old companies like Boeing, who used to champion space travel and the creation of combat and commercial aerial vehicles, while overcoming the high cost of producing rockets, making them reusable and making them safe enough for travel. His name is Elon Musk. Soon he started to get military contracts, earning billions while working with the Pentagon, providing them with a means to launch satellites into orbit. However, the conversation soon moved further than merely launching satellites into the sky, as the Pentagon saw very quickly the potential of Elon's company to create something entirely different from what they used to have, especially since the addition of the behemoth Starship. Now, with Elon's influence in the White House as chief of the Department of Government Efficiency, talks reportedly extended from launching payloads into space for the United States of America to the possible creation of a behemoth bomber that could tower above the United States Air Force bombers like the Boeing B-52 Stratofortress and maybe compete with the Northrop Grumman B-21 Raider. Their rationale was rather simple. Elon is already on the cusp of creating aerial vehicles fast enough to hit Mars by 2026, so why wait for relatively slow bombers, which travel at subsonic speed, when there is a possibility of Elon creating something faster and relatively more lethal? Although SpaceX has never developed a weaponized combat aerial aircraft, being at the adult table at the Pentagon comes with making tough choices and new decisions, something rather different from a favorite niche. Hence, he reportedly agreed, and SpaceX now stands on the precipice, holding the fate of the United States bomber jets in his palms. Although Elon is a genius, What does he know of warfare to be completely entrusted with creating a bomber for the United States? And how does it supposedly compare to his predecessors, especially the B-52 Stratofortress? However, to understand the gravity of Musk's task, we need to look at his competition, the B-52 Stratofortress bomber. The B-52 Stratofortress bomber is a titan of the Cold War, a behemoth that shows up, and the opposition already knows that it is not going to be a good day. As often reported, Boeing really outdid itself on the Boeing B-52 Stratofortress, as it shattered every conventional assumption and belief about the limitations of bombers in the 1950s. The Boeing B-52 Stratofortress is a long-range, subsonic, jet-powered strategic bomber, meaning that it could hit the target not only from seriously ridiculous heights, but it could also have debilitating effects on the opposition, and they would suddenly break their spirits enough to avoid a full-blown or all-out war. For some context, Operation Linebacker 2 in 1972 saw the use of the B-52 Stratofortress bomber in strategic warfare in an attempt to reach a quick ceasefire. The operation took place during the Vietnam War, when the United States unleashed the full strength of its air forces, with the B-52 Stratofortress bomber at the very centerpiece. The operation lasted from the 18th of December to the 29th of December, 1972, during the North Vietnamese War. They unleashed more than 20,000 ordnance that was dropped on military and industrial areas in Hanoi and Haiphong, and at least 1,624 civilians were killed. The operation was the final major military operation carried out by the United States during the conflict and the largest bombing campaign involving heavy bombers since World War II, and Vietnam just didn't know what hit them. After the rain of fire from the bomber, their spirits were broken, so they threw in the towel and decided against an all-out as they stood no chance against a bomber. But what makes the B-52 bomber special, and how was it brought into being in the first place? Let's dial back to November 23, 1945, when the AMC, otherwise called the Air Materiel Command, issued desired performance characteristics for a new strategic bomber that could be used as a long-range bomber without needing a base on foreign grounds, which may be controlled by other countries. They wanted the aircraft to travel at least 34,000 feet, with a crew of 5 or more working the gun turret and a 6-man team that will be working as a relief crew. However, as is popular with a combat aerial vehicle, the ordnances and bombs it carries as payload are of grave importance. What's the point of a bomber jet without enough payload to send anyone running? So they asked for an unspecified number of 20mm cannons and over 4,500 kilograms of bombs. The United States Air Force immediately sent out a bid invitation, inviting all the heavyweights of America's aircraft companies, including Boeing, Consolidated Aircraft, and Glenn L. Martin, to submit proposals. Eventually, Boeing won the 3-horse race and called and got a massive $1.7 million to build a full-scale mock-up of the XB-52 and do preliminary engineering and testing. However, they had trouble at first meeting the specification until much later, when they finally created the B-52 version, with the perfect size and ability to take on payloads. B-52 Stratofortress was designed to have swept wings, potted jet engines, and also crew ejection systems in case of a crash, or if it ever happens that they encounter anti-aircraft resistance strong enough to shoot down the aircraft. However, there are different versions of the B-52 with a little bit of difference in their structural designs. For example, on the B-52D, the pilots in the electronic countermeasure team are ejected upwards, while the crew on the lower deck are ejected downwards. However, the tail gunner, who was stationed at the rear end of the bomber jet, had to manually jettison the gun turret before they then crawled out through the opening, making the survivability percentage extremely low. Enter the B-52G, which was released August 31, 1958, as a potential successor to the B-52D. The G version was stronger and better, and the survivability percentage for whoever manned the gun turret was increased by well over 60%, as they could now eject like everyone else. Although the survivability of the crew has been protected by the changes made to the placement of the gun turret, the aircraft still had a common problem: structural fatigue. In material science, fatigue is the initiation and propagation of cracks in a material due to cyclic loading. Once a fatigue crack has initiated, It grows a small amount with each loading cycle, typically producing striations on some parts of the fracture surface. In the aircraft, the fatigue was accelerated by low flying, 8 times more than it was affected when it was flown higher in the sky. For some context, flying really high in the sky is much easier as there are fewer needs for sharp turns or a need to zoom faster. However, when they fly too close to the ground, there is a need to turn sharper, focus on maneuvering around rocks, and really work the body of the bomber jet. The metal starts to get tired, it cracks, and in some rare cases it bends almost out of shape, requiring the need to fix the plane. The classic wear and tear was starting to make the bomber jets difficult to use for more than 2,000 hours of flight. So in the early 1960s, the United States Air Force created the high-stress program as some sort of checkup program for every B-52 bomber that had been in the sky for over 2,000 hours and was surely going through some structural fatigue. Once they look through the B-52s that had flown over 2,000 hours, they check which one needs to be fixed, and they have stronger pieces added to the body of the bomber, giving it a bit more leverage to fly for that long. As time went on, the Air Force got even craftier, with the creation of wet wings attached to their G and H models of the B-52s. They were called wet wings because they were capable of holding way more fuel than the other models. However, that compromised the structural integrity of the bomber jet even further. The added weight on the wings from the fuel forced the wings to bend out of shape, and they got 60% more fatigue than the B-52D. Once again, the need arose for a solution, so they created the ECP-1050 as a replacement for the wet wings, which increased the durability of the jets and reduced the percentage of quick wear and tear. But there was something more about the bomber, as its sheer size meant that it couldn't perform huge spins or a loop-de-loop like a fighter jet could at an aviation show or in combat. Although the yaw, pitch, and roll were added parts to the bomber plane, it was not built to move like a stunt plane. Instead, the flight controls were focused on vertical stability, even though it has a relatively small, narrow chord rudder, giving it limited yaw control authority. It was almost like having a giant school bus in the air, big, powerful, and with enough room to carry people and ordnances. However, by 1977, they conducted a pacer plank reskinning. The structural fatigue while moving at Mach 1 speed, which is subsonic, was a message to the United States Air Force to make a change. But the United States Air Force continued instead to rely on the jet for its services during war, especially because of its armament as a bomber plane, which is much better than its predecessors. The bomber plan was optimized to carry up to 20 Boeing AGM-69 SRAM nuclear missiles, which are air-to-surface missiles with a nuclear warhead. It had a range of up to 110 nautical miles and was intended to allow United States Air Force strategic bombers to penetrate Soviet airspace by neutralizing surface-to-air missile defenses. It was the perfect response to surface-to-air missiles because it was easier to direct, owing to its precision systems. In a bid to further improve its offensive ability, air-launched cruise missiles, or ALCMs in popular military parlance, were fitted into the B-52 bomber jet. However, after testing of both weapons of mass destruction, the United States Air Force-backed Boeing AGM-86 air-launched cruise missile and the Navy-backed General Dynamics AGM-109 Tomahawk, the AGM-86B was selected for operation by the B-52. However, the continuous development of more models of the B-52 Stratofortress, the Conventional Enhancement Modification, or CEM program, gave the B-52H a more comprehensive conventional weapons capability, adding the modified underwing weapon pylons used by conventional armed B-52Gs, Harpoon and Have-Nap, and the capability to carry new generation weapons including the Joint Direct Attack Munition, or JDAM, and Wind-Corrected Munitions Dispenser guided bombs, the AGM-154, Glide Bomb, and the AGM-158 JAS-M missile. While the B-52 remains a legendary bomber, the times have changed and technology is moving on once again. Although the B-52 bomber remains in use by the United States Air Force when needed, the Northrop Grumman B-21 Raider has come to take its place in the United States Air Force, and the world's about to be introduced to it. But what makes the Northrop Grumman B-21 Raider special enough to become a welcome addition to the new Air Force fleet? The Northrop Grumman B-21 Raider is another masterclass strategic bomber plane being developed in the United States. It is being developed at the behest of the United States Air Force as a part of the Long Range Strike Bomber, or LRSB program, but this time it is a complete upgrade on what the B-52 Stratofortress was capable of. Imagine a bomber jet capable of stealth operations and the ability to deliver conventional and thermonuclear weapons. Well, with the Northrop Grumman B-21 Raider, no one has to imagine anymore. The classified program started in 2011 when the United States Air Force decided it needed a faster bomber plane with more range. So, as is usual practice, they reached out to the heavyweights in the game, offering them a development contract, which was eventually awarded to Northrop Grumman in October 2015. Of course, every company wanted to be in charge of the future of the Air Force fleet, but someone had to win. This time, it was Northrop Grumman. However, a civil war ensued, with Boeing and Lockheed Martin, who submitted losing bids for the project, filing bid protests, claiming they had been wrongfully overlooked for Northrop Grumman. In October 2016, the Government Accountability Office, or GAO, rejected the challenges and sustained the United States Air Force's decision to award the LRSB contract to Northrop Grumman. The Government Accountability Office report revealed that cost was the deciding factor in selecting Northrop Grumman over the Boeing Lockheed Martin team. The Air Force set up an uphill task for Northrop Grumman, telling them that they needed an addition of intelligence gathering, battle management, and interceptor features to the bomber, and a fifth-generation global precision system that guides the release of bombs, nuclear warheads, and all types of payloads it might be carrying. However, alongside India, which is on the cusp of unleashing its sixth-generation aircraft, albeit a fighter jet, the United States is closing in on releasing the first-ever sixth-generation aircraft, but this time, a bomber jet. Fast forward 5 years after it was commissioned to Northrop Grumman, and the Air Force released new renderings of the aircraft, showing a smaller and lighter design than what is typically expected from a bomber. The sheer reduction in size and distinctive flush in blended inlets, with the two-wheel landing gear design, was a revelation of something never seen before. The drawing shows a smaller and much lighter aircraft than its predecessors, like the B-2 and the massive subsonic B-52 Stratofortress. The world had finally had a glimpse at the possibility of the future of bomber planes, with a huge reduction in size being a topic for discussion. However, just a year later, Darlene Costello, the acting Assistant Secretary of the Air Force Acquisition, Technology and Logistics, confirmed that the first two B-21s were under construction at Plant 42. D-Day came on December 2, 2022, when the first-ever B-21 was unveiled at the Northrop Grumman production facilities in Palmdale, California. At the unveiling, Northrop CEO Kathy Warden said that the B-21 is designed with modular, open systems architecture to allow easy upgrades and, potentially, the ability to export components to foreign buyers. The open systems architecture wasn't particularly the most popular form of building jets in the past, especially when a Cold War hero like the B-52 Stratofortress was built. Boeing at the time had relied heavily on the importance of closed architecture systems, which made fixing and upgrading the early B-52s a nightmare for mechanical engineers, who had the pleasure. The open systems architecture is more like building up a Lego character, and all that needs to be done for a quick fix or an upgrade is to simply remove and replace without a need to tear apart the whole structure in the name of rebuilding. On the flip side, the closed structure system is a packed and sealed deal. A fix would need a complete deconstruction of the object before being rearranged, regardless of how massive or small the problem is. Although the popular reasoning is to view the very first tested aircraft as a prototype, the test aircraft was not deemed as one. Rather, it will be converted to operational configuration by the Air Force after the test flight has been completed. In 2023, the officials of the Long-Range Bomber program revealed that the fueling and engine tests took place at the end of the year and were successful, leading to the approval of a low-rate initial production, or LRIP, contract being awarded to Northrop Grumman in January 2024, meaning that there would be a small batch of B-21 Raiders in the production phase and about to be released in 2025. However, new speculations about Elon Musk, the Tesla and SpaceX boss, creating a behemoth bomber of his own, sanctioned privately by the Pentagon, seemed not to be going away. A shocking tale despite the news of the imminent release of the B-21. Although the mystery remains nail-biting and fairly disturbing, as there are no signs of signed documents or public articles that are published to that effect, the speculations remain intact, with specifications of a possible sixth-generation SpaceX bomber capable of a direct lift off the ground and possibly carrier-based, and also due to be released the same time as the B-21 Raiders. Whether Elon Musk's clandestine arrangement to release a SpaceX bomber in 2025 is real or other media noise, only time will tell. The X-44 Manta is changing the game. Unlike the loud jets of the past, this aircraft is built for silence, speed, and stealth. It can appear and vanish before radar catches it, making older warplanes look slow and outdated. As global tensions rise, countries are racing to develop the most advanced aerial weapons, but the United States is pulling ahead, creating planes so futuristic they seem straight out of a sci-fi movie. So what makes the X-44 Manta so special? And why are China and Russia paying close attention? Join us as we break down the cutting-edge technology behind America's newest stealth fighter and why it could reshape the future of air combat. Flying without a tail might sound impossible, but aerospace giant Lockheed Martin once dreamed exactly that. Their extraordinary concept, the X-44 Manta, an acronym for multi-axis no-tail aircraft, wasn't just another military plane design. It represented a complete rethinking of how aircraft could move through the skies, promising maneuvers that would make even eagles jealous. A perfect example is driving a car without a steering wheel, controlling it solely by changing how the engine pushes the driver forward. The Manta achieved something similarly revolutionary in aviation. Scientists at the National Aeronautics and Space Administration in the United States Air Force studied this wingless wonder seriously, believing it might unlock aerial movements previously thought impossible. Directing its thrust in 3 dimensions, up, down, left, right, or any combination. Born from the already impressive F-22 Raptor, this tailless marvel featured a stretched delta wing that resembled a giant arrowhead cutting through clouds. What made it truly special was what it lacked: the familiar tail fins on virtually every airplane. Without these stabilizers, the Manta would have relied entirely on adjusting its engine thrust to control its movement, like balancing on a skateboard purely by shifting weight, but at supersonic speeds. In May 1999, the National Aeronautics and Space Administration in the United States Air Force quietly started working on a bold new aircraft project. The goal was to test new flight technologies without using the traditional tail found on most jets. These new features were meant to improve stealth, control, and performance in the air. NASA hoped to try them out on an F-22 Raptor or even an older F-15 fighter jet. They expected the prototype to begin test flights by the year 2007. NASA believed that the work done on the X-44 Manta could help improve not just military jets like the F-22 and the future Joint Strike Fighter, now known as the F-35, but even faster passenger planes for the public. At that time, engineers were thinking far ahead, dreaming of aircraft that could fly faster, quieter, and with more control than anything that had come before. The government and 2 private companies paid for the project's first steps. Then in June 1999, NASA officially gave the green light and named the aircraft the X-44A. It was an exciting moment in aviation history, as many believed this plane could lead the way into a new era of flying machines. But just 1 year later, funding was cut, and the program was shut down before the aircraft could take flight. However, the ideas didn't completely vanish. Some of the designs in later years, like the proposed FB-22 bomber, were inspired by the same no-tail concept. In many ways, the X-44 Manta's legacy remains in the quiet, powerful jets flying today, and maybe even in the next generation of drones and stealth fighters. When engineers dream big, they don't just aim to improve, they seek to rewrite the rules completely. The documents for the X-44 explicitly called for an aircraft that would leapfrog state-of-the-art, much like how a smartphone didn't just improve the flip phone, but fundamentally changed how people communicate. Lockheed Martin's ambitious goal was simple yet profound. Prove that an airplane could fly perfectly well using only the direction of its engine thrust for control, throwing out centuries of flight control procedures. The X-44 Manta would have been harder to spot on radar screens because it lacked the vertical fins and tail surfaces that typically create distinctive radar reflections. Think of how a smooth stone skips better across water than a jagged one. The Manta applied this principle to radar waves. By removing these traditional control surfaces, the design became stealthier, more streamlined, and more efficient, using less fuel to travel farther. The DNA of the F-22 Raptor ran strong in the X-44, sharing the same powerful engines and body structure. However, the Manta transformed this foundation with its striking delta wing, shaped like a triangle pointing forward, and a complete absence of tail sections. The benefits of this radical approach would have been substantial. The larger triangular wing meant the Manta could carry more fuel than its F-22 parent, allowing it to patrol longer or strike deeper behind enemy lines. By merging the control and propulsion systems into one integrated solution, Lockheed Martin aimed to create an aircraft with fewer moving parts to brake, better fuel economy to extend range, and stunning agility that could make traditional fighters look like they are moving in slow motion. Like a boxer who can dodge punches while barely moving, that's the kind of efficiency and responsiveness the X-44 Manta promised to bring to aerial warfare. The X-44 Manta earned such a distinguished reputation that Lockheed Martin developed another aircraft sharing part of its name, the Lockheed Martin X-44A. This lesser-known cousin is an unmanned aerial vehicle technology demonstrator created by Lockheed Martin's legendary Skunk Works division. Unlike traditional aircraft, the UAV operates without human pilots, crew members, or passengers on board. Instead, these sophisticated flying machines are controlled from a distance or programmed to navigate autonomously, representing a significant advancement in aviation technology. An unmanned aerial vehicle or unmanned aircraft system, commonly called a drone, is a flying machine that operates without humans on board. Instead of having pilots sit in a cockpit, these aircraft are either controlled by someone from the ground using remote controls or fly on their own using pre-programmed instructions. In the 1900s, militaries worldwide developed drones mainly for missions that were too boring, dirty, or dangerous for human pilots. Imagine flying for hours over an empty desert just to see if there are suspicious movements. That is the tedious job perfect for a drone. By the early 21st century, armies everywhere considered drones essential equipment, using them to gather information and carry out missions without risking soldiers' lives. As control technologies improved and production costs decreased, the application of UAVs expanded beyond military use. Today, unmanned aircraft serve countless civilian purposes, including capturing breathtaking aerial photography that once required expensive helicopter rentals. They monitor vast agricultural lands, helping farmers make precise decisions about crop management. The Advanced Tactical Fighter program aimed to create a fighter jet that would dramatically outperform anything before. This new aircraft would use cutting-edge technologies, including sophisticated computer systems, more powerful engines, and special materials that made it nearly invisible. In 1986, the United States Air Force chose two companies, Lockheed and Northrop, as finalists to develop prototype aircraft. Each company would build test planes, the YF-22 and YF-23, to show their ideas in action, and these test planes took to the skies in 1990. After careful testing and evaluation, the Air Force selected Lockheed's design in 1991 to advance into full development. This process, called engineering and manufacturing development, would turn the experimental aircraft into something that could be built in numbers and used in real-world operations. Lockheed's winning design evolved into what people now know as the F-22 Raptor. The F-22 Raptor became the Air Force's premier fighter jet. It combined stealth technology, making it hard to detect on radar, with incredible speed and maneuverability. This gave American pilots a considerable advantage in the sky, as they could see enemy aircraft before being seen themselves. Beyond its primary test goals, the X-44A supported other important projects. In one particularly interesting test, The drone demonstrated how unmanned aircraft might operate on Navy aircraft carriers. Landing on a moving ship at sea is one of aviation's toughest challenges, even for human pilots, so testing these capabilities with a drone represented a significant advancement. These carrier tests helped pave the way for today's carrier-capable drones. What makes the X-44A story so fascinating is how Lockheed Martin developed this significant aircraft completely out of the public eye. While defense companies often work on classified projects, keeping an entire aircraft program secret for almost 2 decades is remarkable. The Manta is an important missing link in drone development, connecting early unmanned aircraft experiments to the sophisticated drones around the world today. Its technologies have influenced numerous current and future aircraft designs, showing how these flying laboratories help advance aviation, even when people don't know they exist. The X-44A is built from nanocarbon fiber, a lightweight but extremely strong material similar to what's used in high-end bicycles and tennis rackets. It runs on a Williams F112 turbofan engine, which works like a miniature version of what powers commercial airliners. What's striking about this drone is its size. With a wingspan of just 30 feet, about the length of a school bus, it's half as wide as its larger cousin, the RQ-170 Sentinel. This compact design made it easier to transport and less visible to radar, which are important features for a military aircraft. Despite its small size, the X-44A packs impressive capabilities. It could reach up to 176 miles per hour, faster than most highway speed limits, making it quick enough to cover large areas on reconnaissance missions. The drone could stay in the air for 1.5 hours on a single fuel load. While this might seem short compared to today's drones that can fly for days, it was enough time to test new technologies and gather valuable data without needing a human pilot on board. Aviation enthusiasts and history buffs can now see this once secret aircraft in person. The X-44A found its retirement home at the National Museum of the United States Air Force near Dayton, Ohio. Located in the Research and Development Gallery inside Building 4, this mysterious drone was finally put on public display in October of 2020. After decades of being hidden from the public's view, visitors can now appreciate this important piece of aviation history. China and Russia are paying close attention to America's X-44 aircraft concept. Both countries are working hard on their military planes, but a comeback or update of the X-44 would give the United States a big advantage in the skies. China's Chengdu J-20 and Russia's Sukhoi Su-57 are their best stealth fighters, but neither uses the same wingless design as the X-44. If America decides to bring this concept back, it could leave these competitors behind in stealth, maneuverability, and battlefield awareness. China is currently developing its next advanced stealth fighter, which might be called the J-25 or a version of the J-31. Their goal is to match American air power. Meanwhile, Russia is working on the Su-75. Russia showed off this fighter jet with big claims. They said this new fighter jet would match the American Manta, but cost less. At its first public display, the jet looked sleek and modern, but there was a problem. The Su-75 has not flown yet. Several years after Russia announced it, the jet is still just a prototype, and no one knows when they will actually make more of them. This delay makes people wonder if Russia can keep its promises about the jet. Russia's defense budget is tight, and sanctions mean they can't get some of the important parts they need. These issues make it harder for them to finish the 75 and start building more. Another problem is its ambitious marketing. The Russian fighter jet was advertised as a low-cost fifth-generation fighter for export, but without proven performance or real battlefield testing, many countries are hesitant. Experts also point out that the Checkmate lacks key stealth features found in more advanced aircraft, like internal weapons bays and engine masking. For now, the Su-75 is more of a PR tool than a real challenge to American or Chinese air power. Until it flies, performs, and delivers, the Checkmate is still just a promise on paper. Another jet Russia is boasting about is the Sukhoi, known as fullback by NATO countries, which is an aircraft that combines fighter and bomber capabilities. It's built for all weather conditions and can fly at supersonic speeds while carrying weapons over medium distances. Although it first flew in 1990 during the Soviet era, it didn't officially join the Russian Air Force until 2014. The Su-34 comes from the Su-27 flanker family, which was originally designed for air combat against other planes. What makes the Su-34 special is its wider cockpit with protective armor. Unlike most fighter jets, where pilots sit one behind the other, this plane places its two pilots side by side, similar to how people sit in a car. Russian engineers designed this aircraft mainly to attack ground and naval targets. It can carry out bombing missions against large fixed and small moving targets. The plane works in daylight or darkness and can operate in bad weather and hostile environments where enemies might be using jamming equipment or shooting back. Besides attacking targets, it can also perform reconnaissance missions to gather intelligence. The Su-34 Russian fighter jet uses a special design with wings in three places: main wings in the middle, small wings up front called canards, and horizontal tail wings at the back. Think of it like a bird with extra control surfaces. Those front canards do two important jobs. They give the plane more lift, like adding extra muscle, and make it more agile, like a gymnast versus a weightlifter. This powerful fighter can carry an impressive arsenal, 12 weapon stations holding between 26,000 and 31,000 pounds of bombs and missiles. That's about the weight of a city bus. It keeps the 30mm GS-31 cannon from earlier models. It can carry 6 air-to-air missiles, mainly for self-defense if enemies approach from behind. The heaviest single weapon it can carry weighs 8,800 pounds, about as heavy as a full-grown elephant. The fighter jet comes with impressive dimensions. It stretches 76 feet, 7 inches long, about as long as 7 tall adults lying head to toe. Its wingspan reaches 48 feet, 3 inches across, similar to the width of a basketball court. When empty, this massive aircraft weighs 49,600 pounds, roughly the same as 6 full-grown elephants. At maximum takeoff weight, it tips the scales at 99,428 pounds, heavier than a fully loaded semi-truck. 2 powerful Saturn engines give this beast its thrust, each providing 30,000 pounds of force when using afterburners. This jet can reach extraordinary speeds. At high altitude, it can fly at 1,200 miles per hour, 1.8 times the speed of sound, or fast enough to travel from New York to Miami in under an hour. Even at sea level, it manages 892 miles per hour. The Su-34 typically cruises at 810 miles per hour, about 3 times faster than a commercial airliner. With a full weapons load, it can fly 680 miles from base and still return safely, covering a round-trip distance roughly equivalent to flying from London to Paris and back. Without weapons, on long-range missions, it can travel up to 2,800 miles on a single fuel load. Regarding altitude, the Su-34 can soar up to 56,000 feet, more than 10 miles high, where commercial planes typically fly at just 6 to 7 miles. The aircraft can handle 9 times the force of gravity during maneuvers. Hence, the pilots experience pressure 9 times their body weight, enough to make most people black out without special training and equipment. The powerful engines of this jet give it a thrust-to-weight ratio of 0.68, providing enough power for impressive climbing abilities and maneuverability despite its heavy frame. For weapons, the fighter jet comes equipped with a Gryazev-Shipunov autocannon with 180 rounds of ammunition. This cannon can fire large shells capable of piercing light armor. The aircraft also features 12 attachment points on its wings and body that can carry between 26,000 and 31,000 pounds of weapons. These can include various rocket pods and missiles, the B-8 pods that fire 20 S-8 rockets, B-13 pods for 5 larger S-13 rockets, and sophisticated air-to-air missiles like the R-73 and R-77 for defending against enemy fighters. This extensive arsenal makes the Su-34 one of the most versatile combat aircraft in Russia's military lineup. The Su-34 has several problems. First, it is built on old Su-27 designs, making it hard to add new technology to the jet. It also does not have stealth features like newer jets. This means radar can easily spot it during missions, which is dangerous in modern war. The Su-34 is also very big and heavy. While it can carry many weapons, this extra weight makes it slower and less nimble than other jets in close combat. The world's big military powers, Russia, the United States, and China are engaged in a contest they never discuss openly. Every new fighter jet, missile test, or space launch is part of this competition. These countries say they are just updating their equipment, but their actions show something else. When America developed something like the X-44 Manta aircraft, China and Russia quickly work on their versions to keep up. It's a high-stakes game of follow the leader that shapes military technology worldwide. The A-10 Warthog has earned a tough reputation over the years, built like a tank and feared by enemies on the battlefield. So when the United States pumped $3 billion into upgrading it into a Super A-10, expectations were sky high. But things didn't go as planned. Instead of a stronger, deadlier version of the Warthog, the project ran into serious trouble, and the outcome left many in shock. So what exactly went wrong? And what does this mean for the future of the A-10? Join us as we discuss the features and failures of the U.S. new $3 billion Super A-10 Warthog. Just a few years ago, the United States Air Force came close to shutting down its entire fleet of A-10 Thunderbolt IIs, widely known as Warthogs. Back in 2014, the then Chief of Staff, General Mark Welsh III, stated that retiring the A-10 completely was necessary to significantly reduce the defense budget. He explained that the funds and personnel saved would be redirected to establishing new F-35 units. According to Welsh, retiring the A-10 could save around $3.7 billion over the 5-year defense program, plus an additional $500 million in upgrades that would no longer be needed. Despite the A-10's legendary reputation and battlefield dominance, the aircraft does have critical shortcomings, and some of them threaten its future in active service. Originally developed during the 1970s to hunt and destroy Soviet tanks, the A-10 was built without an integrated targeting radar. This design decision is now one of its most limiting factors, especially in the era of precision-guided weapons. While many A-10 Warthogs have since been upgraded with targeting pods mounted on their centerline, these enhancements still fall short of offering the capabilities provided by a dedicated onboard targeting radar system. This shortfall has unfortunately played a role in serious battlefield mistakes. One of the most significant issues is the aircraft's inability to consistently confirm target identities from the air. This has led to multiple friendly fire incidents. Two of the most high-profile cases involved an A-10 attacking a British armored column due to misidentification, and another similar event in which U.S. Marine Corps vehicles came under fire from an A-10. These tragic errors have raised important questions about the aircraft's suitability in complex mixed-force environments. Another known advantage of the Warthog is its impressive ability to linger over the battlefield for long periods, a key strength in close air support. However, this endurance comes at a cost. The aircraft's relatively slow speed makes it a more vulnerable target for enemy fire. Threats like small arms and portable air defense systems, particularly shoulder-launched missiles known as man-pads, pose a serious danger. Because the A-10 flies slower than modern jets, it has less time to respond with defensive countermeasures like flares and chaff once a missile is launched. Additionally, the A-10 is not built for maneuvering in air-to-air engagements or when dodging incoming threats. The aircraft lacks afterburners, which limits its acceleration, and its turning capability is not as sharp as that of more agile fighter jets. This puts the Warthog at a disadvantage when facing modern missile threats, especially in contested airspace. As a result, the A-10 is usually confined to operations where U.S. forces already control the skies, ensuring the aircraft can safely carry out its mission without having to face advanced enemy fighters. Finally, perhaps the most significant challenge to the A-10's continued relevance is that other aircraft across the U.S. military inventory can now perform many of the same close air support roles. Multi-role fighters like the F-35, F/A-18, F-16, and even the F-22 can deliver precision strikes. Meanwhile, attack helicopters such as the AH-64 Apache, An unmanned aircraft like the MQ-9 Reaper can carry out low-altitude support missions with similar, or in some cases greater, loitering capabilities. Taken together, these limitations show why the A-10 remains a remarkable aircraft, but also face growing questions about whether it's still the best tool for the evolving needs of modern combat. The Air Force pushed for the F-35A Lightning II to take over the A-10's role, claiming that the newer jet was better suited for modern threats. As America's involvement in long wars like Afghanistan decreased, some leaders argued that close air support specialists were no longer as essential. However, this argument didn't sit well with everyone. Many lawmakers in Congress strongly opposed retiring the A-10, warning that doing so would harm the Air Force's ability to support troops on the ground. Some even pushed for a fly-off, an official test between the A-10 and the F-35, to determine whether the newer jet could truly replace the older warhorse in close support missions. In the year 2014, as the U.S. Air Force considered phasing out its fleet of A-10 Thunderbolt IIs, events in the Middle East were quickly reshaping that decision. Around the same time, Operation Inherent Resolve, the American-led mission aimed at defeating the so-called Islamic State in Iraq and Syria, was gaining momentum. As the conflict intensified, pressure mounted on the Air Force to increase its presence and contribution to the campaign. Back in Washington, D.C., the fiscal year 2015 defense budget became a critical turning point. Both the House and Senate Armed Services Committees included specific clauses that blocked any immediate plans to retire the A-10 fleet. This combination of battlefield urgency and legislative action created a situation that essentially saved the A-10 from being cut. That October, the Indiana Air National Guard's 163rd Fighter Squadron, nicknamed the Black Snakes, was deployed to the Central Command region as part of a theater security package. Initially sent to Kuwait, the unit was swiftly redirected to Afghanistan to support the safe withdrawal of U.S. Army forces from forward operating bases scattered across the war-torn country. However, after only about a month in Afghanistan, shifting priorities and growing threats led to another reassignment. The squadron was ordered back to Kuwait to join the growing battle against ISIS. Once back in the region, the A-10s were immediately placed into combat roles. Their reintroduction to active fighting provided a powerful reminder to senior Air Force officials of the aircraft's value. As the campaign evolved, more A-10 squadrons were called into service. Their roles included delivering precision close air support to ground forces and flying protective missions for combat search and rescue teams during joint coalition operations. The A-10's effectiveness came from its specialized design. Built around a massive 30mm cannon, it was made for survivability and precision in ground attacks. Over time, its systems and weaponry had been upgraded, allowing it to carry modern smart munitions. But more than its firepower, the aircraft's ability to loiter over battlefields, absorb damage, and continue flying made it a favorite among troops on the ground. Despite earlier claims that the A-10 was outdated and vulnerable in high-threat environments, its performance in Operation Inherent Resolve painted a different picture. While new aircraft like the F-35 were being considered as replacements, many in the military and in Congress argued that the A-10 still filled a critical role that no other platform could match. The effort to retire the A-10 set off a chain reaction that affected how the aircraft was supported and upgraded. When discussions of cutting the fleet gained traction, testing and development work began to grind to a halt. The active-duty A-10 fleet, which was being tested and evaluated by the 422nd Test and Evaluation Squadron at Nellis Air Force Base in Nevada, and managed by the A-10 Program Office at Hill Air Force Base in Utah, saw those operations nearly shut down. But as Operation Inherent Resolve escalated, everything began to shift once again. By the summer of 2016, it became clear that the A-10 still had a role to play. Work resumed on critical updates to the aircraft, and the Air Force began reversing its earlier drawdowns. Although the planned retirement of the A-10 temporarily disrupted supply chains, upgrades were quickly put back on schedule. One of the key enhancements came in 2017 when the Lightweight Airborne Recovery System, or LAR's version 12, was installed across all active-duty Air National Guard and Air Force Reserve Command A-10s. According to Major Matthew Catting, the A-10 test director for the 59th Test and Evaluation Squadron, This system allowed pilots to communicate much more effectively with personnel on the ground, such as downed aviators and pararescuemen. The technology was included in Operational Flight Program Suite 8 and is now integrated into the aircraft's Central Interface Control Unit, making it a vital component in combat search and rescue missions. Due to limited funding, A-10 testing efforts have become more collaborative. The active duty testing units, such as the 422nd and 59th Test and Evaluation Squadrons, now work closely with the Air National Guard and Air Force Reserve Command Test Center, known as AATC, based at Tucson Air National Guard Base in Arizona. This unified approach helps stretch resources while continuing to push forward with essential development. Today, the U.S. Air Force still operates a fleet of 281 A-10s. Despite multiple efforts to reduce this number, the aircraft continues to hold on thanks to both its battlefield relevance and the backing it receives from advocates in Congress. The proposed fiscal year 2021 budget had aimed to eliminate 44 A-10s, equivalent to the size of 3 full squadrons. But this move has also faced resistance and could be blocked like previous attempts. With support growing and battlefield needs evolving, the A-10 is now receiving long overdue updates that promise to keep it mission-ready for years to come. These enhancements aren't just about better performance, they also reflect a shift in thinking. Instead of phasing the jet out, the Air Force appears to be embracing its strengths and doubling down on its value in the modern combat environment. With upgrades now moving forward at full speed, the Warthog is proving once again that it's far from obsolete and still has plenty of bite left. The A-10 has seen such a revival in purpose and relevance that a new initiative, called the Common Fleet Initiative, is being developed to ensure the aircraft remains in service and combat ready through at least the year 2035. At the heart of these improvements is the need to make the A-10 more survivable in modern, highly contested battle environments. That means pilots must be able to strike from a safe distance using advanced standoff weapons and revised combat tactics. Rather than flying directly into dense air defense zones, A-10 pilots will soon be able to engage certain threats from extended ranges using precision-guided munitions. Once enemy air defenses are neutralized, the A-10s can shift back to their more traditional role, delivering close air support with devastating accuracy. This shift is not just about hardware upgrades, it's also about enhancing tactics to ensure every mission is carried out with maximum effectiveness and survivability. Major Matthew Kading, a key figure in A-10 test operations, emphasizes that survivability isn't just tied to equipment. It's about going into combat with the most current and lethal tactics, he explains. What makes the 422nd and 59th Test and Evaluation Squadrons unique, along with the 53rd Wing as a whole, is their comprehensive approach to innovation. They don't just upgrade systems, they refine the way the aircraft is flown and fought. Currently, the 422nd Squadron is involved in multiple tactics development and evaluation projects, also known as TD and EES. These initiatives are part of the Air Combat Command's Tactics Improvement Proposals Program, often shortened to TIPs. One such tie-up focuses on improving survivability during night missions at medium altitudes and exploring how modern night vision goggles can enable safer low-altitude operations after dark. This re-evaluation could allow the A-10 to execute its main missions at night, a capability that has become more feasible due to improvements in night vision technology. Other ongoing projects include adapting combat search and rescue tactics, refining maritime target engagement using the AGR-20 Advanced Precision Kill Weapon System, commonly called APKWS, and boosting the A-10's performance from austere or minimally supported airfields. The AGR-20 APKWS-2 is a precision-guided version of the old 2.75-inch folded fin aerial rocket and was added to the A-10's arsenal back in 2013. Major Kading also mentioned the enhancements that came with Suite 9, which was introduced in 2019. This software upgrade integrated the Situational Awareness Position System, or SAP, into the Operational Flight Program. With SAP, forward air controllers, known as JTACs, can digitally report their own positions to avoid friendly fire incidents, especially when using inertially guided weapons. Suite 9 also introduced the ability to strike multiple targets with precision weapons in a single command. Pilots can now drop up to 6 munitions with one press of the pickle button. Altogether, these upgrades signal a bold future for the A-10, one focused on survivability, adaptability, and tactical superiority. With the latest improvements to the A-10 Thunderbolt II, pilots can now release multiple weapons on different targets with just a single button press during one flyby. In the past, this required significant manual input from the pilot. Now the aircraft can determine whether multiple bombs, like the 500-pound class GBU-38 and GBU-54, or the 2,000-pound GBU-31, can hit their intended targets on a single pass, all while reducing pilot workload. One major part of this modernization came with Suite 9, which included upgrades to the pilot's helmet. A new sight system, called Hobbit, builds on the Thales Visionix Scorpion helmet that A-10 pilots began using in 2013. Hobbit uses a canopy-mounted optical tracker, a series of small dots, to more accurately follow the pilot's head movements, improving targeting efficiency and responsiveness. But the biggest leap since the original A-10 Alpha to A-10 Charlie upgrade in the early 2000s is just around the corner. Back then, the shift brought precision-guided weapons, a semi-digital cockpit, and laser targeting pods. Now Suite 10, scheduled to roll out in the spring of 2021, marks another foundational step forward. According to Major Matthew Kading, this upgrade will offer improved ability to strike multiple targets with different weapon types on a single pass. Full integration of the AGR-20 Advanced Precision Kill Weapon System means that rockets can now be used at their maximum range with precise onboard aiming solutions. The GBU-31V3 JDOM integration brings expanded fuse compatibility and improved feedback, so pilots can better confirm the accuracy of their strikes. Another key feature of Suite 10 is enhanced data sharing. A-10s will now be able to exchange real-time threat data through their onboard data links, giving all flight members better situational awareness and improving chances of survival during missions. Looking ahead, Suite 11 is already in developmental testing with the 40th Flight Test Squadron at Eglin Air Force Base in Florida. It will be the first suite built using agile development techniques, allowing for faster delivery of future updates. Planned enhancements in Suite 11 include new hardware and software systems, a high-resolution display system, integration of the GBU-39 small-diameter bomb, three-dimensional audio for better spatial awareness, jam-resistant GPS, and upgraded ARC-210 radios. Additionally, a new mapping system will improve navigation and target identification. The HRDS is a game-changer. Replacing the old analog six-pack instruments in the cockpit, it introduces an 11.6-inch digital color display with high-definition resolution. This new screen will show enhanced footage from targeting pods and sharper map imagery, significantly improving visibility in poor weather or low-light conditions. This upgrade is vital for safer navigation and better precision in instrument meteorological conditions. He also highlights that the small-diameter bomb will give the A-10 a four-fold boost in standoff range, letting pilots hit high-value targets while staying out of reach of enemy ground defenses. On July 25, 2019, the United States Air Force wrapped up a major milestone, successfully completing a project to install new wings on a portion of its A-10 Charlie fleet. This effort began back in 2007 when Boeing secured a $1.1 billion contract to manufacture 173 sets of replacement wings. These new wings were built to endure up to 10,000 equivalent flight hours without needing a depot-level inspection. That impressive durability is expected to keep these modified aircraft flying through the year 2030 or even beyond. The success of the initial wing replacement project led to an additional round of funding in fiscal year 2018. This second phase aims to deliver another 112 wing sets, intended for the remaining A-10 Charlies that did not receive upgrades in the first round. These new wing kits are being acquired under a special effort known as the A-10 Thunderbolt Advanced Wing Continuation Kit, or ATACK program. While these structural improvements are helping to extend the life of the Warthog, one long-standing idea remains on hold: the re-engining of the A-10. For years, there have been calls to equip the aircraft with updated or more powerful engines, particularly to replace the General Electric TF-34 engines, which currently run slightly below their original performance due to detuning. However, this ambition is not part of the Air Force's current modernization plans. Even without new engines, the A-10 is receiving significant upgrades that will keep it as a top-tier close air support platform for at least another decade. Advanced cockpit systems, weapon integrations, sensor improvements, and survivability upgrades are all coming together to ensure that the A-10 remains relevant in future battlefields. Additionally, the use of modern manufacturing techniques and new suppliers may help the Air Force restore or slightly improve the original engine output without needing to redesign the aircraft's power plant entirely. Whether or not the A-10 stays in service long-term will largely depend on future decisions by the Air Force. For now, all signs point to continued investment in the A-10 fleet. With its upgraded wings, extended flight hours, and new mission systems, the aircraft is better positioned than ever to support ground forces in the most demanding environments. Unless there's a dramatic shift in Air Force priorities, the Warthog will likely remain a vital part of American air power for many years to come. There is a lot at stake for Russia, and that's the idea. The United States has now rolled out a new generation of stealth bomber that doesn't just test limits, it changes them. This stealth bomber is made to go undetected, strike from incredibly long distances, and survive within the most contested airspace on the planet, even in today's modern warfare. What does this mean for the world as military technologies evolve? Is the United States taking a defensive or an offensive technological leap forward in global affairs? Join us as we explore the hidden powerhouse that's designed to strike without warning. Ever since the Cold War wrapped up, America has looked at its big bombers as more than just flying weapons. These aircraft serve as massive calling cards that communicate global reach and serious intent. The trusty old B-52 has been around forever. The sleek B-1B could really move. And then there's the B-2 Spirit. This almost alien-looking aircraft costs more than some countries' entire defense budgets. For decades, these planes owned the skies. They could haul nuclear weapons anywhere on the planet, and most enemies knew better than to mess with them. But time doesn't stand still, especially in warfare. Those aircraft began to show their age. And meanwhile, other countries weren't just sitting around. They were building air defense systems that could pose a real threat to America's flying fortresses. It became evident that the United States needed something completely fresh. Not just another upgrade or patch job, but a bomber built from scratch to handle whatever the next few decades might throw at it. After more than 30 years without designing a new strategic bomber, America finally had its answer, the B-21 Raider. And they have been working on this thing in almost total secrecy. The kind of project that makes people wonder what else is being developed behind closed doors. The B-21 is not just another bomber, it is a game changer in military aviation. It is built for long-range missions, designed to stay undetected, and capable of striking targets with incredible precision. In today's world, where speed and stealth matter more than ever, this aircraft is made to operate where others can't. However, reaching this point was not easy. The technology, design, and strategy behind it are the result of years of testing and innovation, shaping the way the United States approaches air combat. Back in the 1970s, the United States set out to develop a new bomber that could eventually replace the B-52, which had already secured its place in history. The result was the Rockwell B-1, a supersonic bomber built for speed and low-altitude missions, designed to evade enemy radar. At the time, it was a significant advancement, but technology continued to evolve. Radar systems became more precise, missiles got deadlier, and the challenges for stealth bombers continued to grow. As threats changed and global tensions shifted, so did American priorities. Every new bomber was more than just a reaction to emerging enemies. It was a message. By 1977, people started losing faith in the whole idea of strategic bombers. President Carter's team looked around and saw these increasingly sophisticated air defense systems popping up everywhere. Cruise missiles were also becoming a bigger deal, and bombers seemed like they were heading toward irrelevance. The B-1 program, which had been this shining example of next-generation speed and raw power, got shut down completely. Then Reagan walked into the White House, and everything flipped. Cold War tensions cranked back up to 11, and suddenly the arms race was in full swing again. The B-1 program came roaring back to life, but this time as the B-1B Lancer. Sure, they had to dial back the top speed to Mach 1.25, but that compromise bought them something valuable. The aircraft received significantly improved protection against air defenses, and they could be built quickly. Within 6 years, they'd rolled out more than 100 units. It was classic Reagan-era thinking. While the B-1B was entering service, another project was taking shape behind closed doors. Northrop Grumman engineers, working under extreme secrecy, were building something even more advanced, an aircraft that would not just avoid detection, but would practically disappear from radar. The result was the B-2 Spirit, a breakthrough in stealth technology. Its flying wing design, lack of a vertical tail, radar-absorbing coatings, and heat-dampening structure made it one of the most complex aircraft in the world to track, let alone intercept. It was nearly invisible, living up to the name Spirit in every way. That level of stealth came at an enormous cost. Each B-2 was initially priced at about $2,130 million, and today, when adjusted for inflation, that figure jumps to over $4,300 million. Lawmakers were shocked, and with growing pressure to control defense spending, Congress cut the original plan to build 132 bombers down to just 21. Even the hangars had to be re-engineered with tightly controlled climate systems just to preserve the aircraft's stealth coating. Every aspect of the B-2's development was a financial and logistical challenge, one that sparked both admiration and debate. Despite its massive cost, the B-2 showed exactly why it was worth every dollar. It could fly deep into enemy territory without being detected, making it a key player in precision strikes and critical missions. But it wasn't just another bomber, it was a statement of American technological superiority. In modern warfare, visibility can mean vulnerability, and the B-2 proved one thing: the most dangerous threat is the one that goes unnoticed. During the North Atlantic Treaty Organization bombing campaign against Yugoslavia in 1999, just 3 B-2 Spirit bombers took off from Missouri. They carried out about 11% of all coalition airstrikes. These long-range missions were executed with pinpoint accuracy and 0 losses, leaving both allies and adversaries in awe. Later, the B-2 proved its capabilities again in Iraq, Afghanistan, and Libya, launching strikes directly from United States soil and returning home, all without relying on foreign air bases. It was a force to be reckoned with, fast, precise, and nearly unstoppable. Over time, even the Spirit's stealth started to show its limits. The B-1B Lancer was already struggling, with only half of its fleet operational by the early 2010s, and the B-2 wasn't immune to the pressure either. Advancing radar systems, multi-frequency detection, and data from satellites and drones began exposing weaknesses in its once undetectable design. What was once an invisible shield became a sophisticated cloak, still effective, but no longer perfect. This raised serious concerns for the United States Air Force Strategic Command. It was time to rethink the future of stealth bombers. By the 2010s, it is evident that not all bombers would continue serving the same role. The B-52, first introduced in the 1950s, kept getting upgrades, with plans to keep it flying for decades. At the same time, the B-1B was removed from the United States nuclear strike system. The B-2 was still a powerful machine, but its high cost, complexity, and aging stealth technology made it less reliable for large-scale missions. It was clear that the next generation bomber had to be something new, stealthy, durable, adaptable, and free from the hefty price tag and maintenance challenges of the B-2. As warfare advanced, the need for a new bomber became urgent. Hypersonic missiles, space-based weapons, high-powered lasers, smarter air defenses, and artificial intelligence capable of learning enemy tactics were making older strategies obsolete. Technology was evolving fast, and for the United States to stay ahead, it needed a bomber built for the future. After years of development, that solution finally arrived: the B-21 Raider, designed to remain hidden and untouchable. The United States Air Force realized that just making another stealth bomber wouldn't cut it. The world was shifting rapidly, and the threats were evolving just as fast. They needed something completely different, a strategic bomber that could not only survive in current combat zones, but dominate whatever conflicts might emerge in the future. This vision became reality in 2011 when they launched the Long-Range Strike Bomber program. The goal was straightforward: create a next-generation intercontinental stealth aircraft that could handle anything. But this bomber would do much more than just drop conventional and nuclear weapons. The aircraft would serve multiple roles. It could gather critical intelligence behind enemy lines, coordinate complex battlefield operations across vast distances, intercept enemy aircraft when needed, and adapt to whatever new missions emerged around the globe. Essentially, they were building a flying command center that could strike, spy, and coordinate, all while staying completely invisible to enemy radar systems. The military understood that future conflicts wouldn't look like past wars. They needed an aircraft that could evolve with changing circumstances rather than one designed for a single specific threat. With goals that big, the Air Force had something specific in mind: a multi-role war machine they called a sixth-generation global precision strike platform. The idea was to merge stealth technology with advanced sensors and incredible range, giving military commanders the power to spot and hit threats from virtually anywhere on Earth. When it came time to choose a contractor, they selected Northrop Grumman. This was the same company that built the famous B-2 Spirit, so they knew their way around stealth bombers. But this time around, Northrop Grumman made a key promise: they would keep costs under control. The B-2 had been a public relations nightmare because of its enormous price tag. People couldn't believe how much each aircraft cost, and it created serious political problems for the program. Northrop Grumman understood they couldn't afford another financial disaster like that. This project wasn't just about creating an incredible piece of military hardware. It was also about developing cutting-edge technology. It was also about proving they could deliver cutting-edge performance without breaking the bank. The company needed to rebuild confidence in both its engineering capabilities and its financial management. Success meant delivering a bomber that worked brilliantly and cost what they said it would cost. The B-21 Raider might look a lot like the B-2 Spirit at first glance, but it's far from just an upgrade. When designing a stealth flying wing, engineers have two choices: stick with what works or take a risk on flashy new concepts that often fail in real combat. The Raider follows a proven design but pushes it further. It's closer to the original early blueprints of the Advanced Technology Bomber program than the final B-2. Unlike the Spirit's jagged trailing edges, the B-21 has a smoother, more refined shape, built for high-altitude missions and optimized to stay nearly invisible to radar from every angle. Flying at higher altitudes gives the Raider a significant edge, like standing on top of a mountain with a set of binoculars. From up there, visibility is unmatched, allowing it to detect and track things others might miss. The same principle applies to the B-21. Operating at higher elevations enhances its sensors and communication systems, making it easier to gather and share critical data. This isn't just about keeping the bomber safe. It's about giving nearby friendly forces a real-time, full-picture view of the battlefield, like a lookout scanning the entire sky from above. This capability becomes crucial on modern battlefields, where making the right decisions quickly often depends on having fast, reliable information. The B-21 is being built to work closely with other advanced aircraft, particularly the sixth-generation fighter jets that are part of the next-generation air dominance program. When these aircraft operate together, they form a connected network of platforms that can instantly share information. Instead of each plane working alone, they function as parts of a larger system. This approach enables them to coordinate attacks, share threat warnings, and respond to changing situations much faster than traditional aircraft operating independently. The focus isn't just on making individual aircraft stronger or faster. It's about creating a cohesive force that works together, adapting in real time based on shared intelligence across an entire network. The B-21's biggest advantage is its open architecture, meaning it was designed to evolve. As technology advances, whether it's hypersonic missiles, high-energy lasers, or next-generation artificial intelligence, the B-21 can be upgraded without needing a completely new design. That adaptability keeps it ahead of emerging threats for decades. unlike older bombers that became outdated due to rigid structures. In a rapidly changing battlefield, its ability to stay relevant makes it a lasting investment in American air power. One of the most significant upgrades is its extended range. The B-21 is designed to cover thousands of miles without needing to refuel, making it a game-changer for missions deep inside heavily defended territory. Today's adversaries are building advanced anti-access and area denial zones, so long-range endurance isn't just an advantage, it's essential. By flying higher, traveling farther, and operating smarter, the Raider isn't just built to survive in hostile airspace. It's built to dominate it. The B-21 Raider isn't just built for long flights. It's designed to stay airborne longer than any bomber before it. Current U.S. bombers already take on marathon missions lasting over 24 hours, but the B-21 is expected to extend that even further. A big reason for that is fuel. Even though it's about 2/3 the size of the B-2 Spirit, it has redesigned shorter internal weapons bays, which free up space for extra fuel storage. That added capacity, combined with a more compact, efficient layout, has even earned it the nickname Stealth Gas Tank among some. Its fuel efficiency isn't just about storage. Unlike the B-2, which relies on 4 engines, the Raider runs on 2, a design choice that cuts fuel consumption without compromising performance. Northrop Grumman hasn't officially revealed which engines power the B-21, but this twin-engine setup plays a key role in maximizing efficiency. When a person combines that with its long-range capabilities and high-altitude flight profile, you get an aircraft built for extended missions, crossing oceans and continents without needing to refuel mid-flight. One of the B-21's most unique features is its recessed air intakes, carefully built into the bomber's body. This isn't just about looks, it's a crucial part of reducing radar visibility from almost every direction. Air intakes have always been a challenge in stealth aircraft design because they tend to disrupt the smooth surfaces needed to deflect radar waves. But on the Raider, engineers have found a way to integrate them without compromising stealth, proving just how much technology has evolved since the B-2. It's a small detail with a significant impact on survival in contested airspace. Even though its sleek design might look like it limits its payload, the B-21 is built to carry serious firepower, especially for its most critical mission. A key goal of the Long-Range Strike Bomber program is to make sure the Raider can deliver advanced nuclear weapons deep into enemy territory. To do that, it's equipped with the stealth-capable AGM-181 long-range standoff cruise missile, designed to hit targets from far outside hostile defenses. In the end, the B-21 isn't just efficient, it's powerful, precise, and nearly impossible to detect. By December 2022, the United States Air Force had already run at least 9 test flights of its newest advanced missile system. Just 3 months later, in March of the following year, that missile cleared a critical design review, moving one step closer to being deployed with both the B-21 Raider and the B-52 Stratofortress fleets. But that's just part of the larger plan. According to Air Force Secretary Frank Kendall, the B-21 may carry more than just conventional or nuclear weapons. It could also be equipped with directed energy systems, including high-powered combat lasers currently being developed by Lockheed Martin. These next-generation weapons are part of a larger strategy shift. Alongside the B-21 Raider and the upcoming 6th-generation fighter jets from the Next Generation Air Dominance program, the Air Force is building what it calls a family of systems. A significant piece of this network will be collaborative combat aircraft, autonomous wingman drones powered by artificial intelligence. To develop these drones, the Air Force plans to invest nearly $9 billion between 2025 and 2029. The goal is to reduce the number of pilots needed and create squadrons where manned and unmanned aircraft work together seamlessly. Right now, flight testing has already started with the first B-21 prototype. Northrop Grumman has 5 more Raiders being built at various stages. Plus, they're also constructing some non-flying versions just for ground testing purposes. The plan is ambitious. They want at least 100 B-21 Raiders ready by the early 2030s. When considering the complete program over the next 30 years, encompassing all research, building, and maintaining these planes, the total cost exceeds $203 billion. Even with that massive overall price tag, Each B-21 should cost around $700 million. That might sound like a lot, but it's a considerable improvement over the B-2 Spirit, which ended up costing over $2 billion for each aircraft. This dramatic cost reduction demonstrates that Northrop Grumman has learned valuable lessons from the B-2 program. They figured out how to build advanced stealth bombers without the financial disasters that plagued earlier projects. Getting more capability for less money means the military can afford to buy enough of these aircraft to make a real difference. With that level of investment, there's a lot on the line. Can the United States Air Force pull off a thoroughly modern bomber fleet by 2030 while also rolling out sixth-generation fighters and autonomous drones? One thing is clear, the next few years will shape the future of air dominance, and the battle for the lead is already underway. £30,000 of pure destruction rained down from invisible bombers in the dead of night. American B-2 Spirit stealth aircraft delivered the most devastating blow to Iran's nuclear program in history, dropping massive bunker-buster bombs that shook the earth for miles. The secret mission took 20 years to plan and 36 hours to execute. But what happened next changed everything. Will Iran strike back? Can America prevent nuclear war? Join us as we find out what went down when the United States fighter jets dropped the hammer on Iran. 0210 hours, Tehran time. 7 invisible ghosts sliced through Iranian airspace at 30,000 feet. No radar signature, no engine sound, and no prior warning. The lead Bravo 2 Spirit bomber approached its target, the Fordow fuel enrichment plant, buried 600 feet beneath solid rock 60 miles south of Tehran. Inside the cockpit, 2 aviators prepare to make history. Their aircraft carries 2 GBU-57 massive ordnance penetrators. Each bomb weighs 30,000 pounds. Each contains enough explosive power to level a city block. The mission clock reads 0640 Eastern Standard Time back in Washington. Defense Secretary Pete Hegseth watches real-time satellite feeds from the Pentagon. Chairman of the Joint Chiefs, General Dan Kane, monitors radio frequencies. Radio silence from the strike package means everything proceeds according to plan. 18 hours earlier, these same bombers departed Whiteman Air Force Base in Missouri. The pilots flew through the night, crossing continents without detection. Multiple aerial refueling operations kept the massive aircraft airborne. The mission requires 36 hours from takeoff to landing, the longest operational Bravo 2 flight in United States history. Now comes the moment that 2 full decades of secret engineering have been building toward. Hidden in plain sight, deep inside heavily guarded hangars, the weapon known as the GBU-57 finally gets its call. This isn't just another bomb, it's America's most classified bunker buster. Built with a special high-strength steel alloy, it's designed to do what ordinary bombs cannot. While other weapons explode on the surface, this one drills down through layers of rock and reinforced concrete, punching deep into targets buried far below ground. It's made to take out hardened facilities, those hidden command centers that enemy forces think are safe. But that night, the illusion ended. For the first time, the GBU-57, the so-called invisible hammer, is unleashed in real combat. Not in a test range, not in a simulation, but on a real enemy position. And what happens next changes the game. Target acquisition complete. Bomb bay doors open on the lead aircraft. 2 massive shapes drop into the darkness below. GPS guidance systems steer each penetrator toward precise impact coordinates. The weapons accelerate through thin mountain air, building devastating kinetic energy. Impact occurs in 3 seconds. The Earth shakes for miles in every direction. Deep underground, the first GBU-57 punches through 600 feet of rock and reinforced concrete before its warhead detonates. The second bomb follows an identical trajectory, ensuring complete destruction of the buried facility. Seismic monitors across the region register the underground explosions. 6 more Bravo 2 bombers execute identical attack runs across 3 separate nuclear sites. Natanz receives 4 more invisible hammers. Isfahan gets struck by submarine-launched Tomahawk cruise missiles. 75 precision-guided weapons find their targets within 25 minutes. Iranian air defenses never activate. No surface-to-air missiles launched. No fighter aircraft were scrambling to intercept. The strike package exits Iranian airspace as silently as it entered. Mission accomplished. Real-time satellite imagery streams into Pentagon situation rooms. Initial battle damage assessment reveals catastrophic destruction at all three facilities. Smoking craters mark locations where Iran's nuclear program operated just minutes before. Years of uranium enrichment capability vanish in less than half an hour. But then something unexpected flashes across the satellite feeds. A faint heat signature. At first it looks like static, maybe a glitch. But within seconds the signal grows stronger. Movement is detected at a fourth location, a site that was not on the original strike list. No known weapons, no confirmed command presence. It was supposed to be empty. Inside the operations center, intelligence analysts freeze. Eyes lock on their monitors. Fingers fly across keyboards. Multiple surveillance systems now point toward the new target. What they see makes their stomachs drop. Dozens of vehicles, unusual power activity. Underground entrances are disguised beneath old structures. Whatever's happening there, it's not routine. This site doesn't match any official records. It wasn't in satellite archives. It's as if it never existed until now. One analyst pulls up thermal overlays, another checks past drone footage. The pieces start to fit, and the picture is disturbing. The movement isn't defensive, it's logistical. Something is being prepared, moved, or hidden, fast. Then it hits them. This might be a shadow facility, part of a secret layer of Iran's nuclear program that was never disclosed. The kind of site meant to stay buried from the world. A backup plan, or worse, a next phase. Within minutes, calls go out. Defense officials huddle behind closed doors. Maps are redrawn. Strike options are reassessed. Because now the mission isn't over. It may have just begun. The smoking craters hide a deeper secret. America's most classified weapon just revealed itself after 2 decades of absolute silence. Defense Threat Reduction Agency Headquarters, McLean, Virginia. 20 years ago today, engineers began designing the ultimate bunker buster. Codename, Massive Ordnance Penetrator. Classification level, beyond top secret. The weapon system emerges from 2 decades of silence like a ghost materializing in broad daylight. Each GBU-57 measures 20 feet long and weighs 30,000 pounds, larger than most automobiles. The warhead contains 5,300 pounds of high explosives wrapped in specially forged steel alloy. This steel penetrates 600 feet of reinforced concrete before detonation. Only one aircraft in the world carries this weapon, the Bravo II Spirit stealth bomber. Boeing engineers spent 9 years integrating the massive penetrator with the bomber's internal weapons bay. Each Bravo II holds exactly 2 GBU-57s, no more, no less. The aircraft's stealth design keeps the radar cross-section smaller than a flying bird, despite carrying 60,000 pounds of bunker-busting explosives. Testing began in fiscal year 2024 at Eglin Air Force Base, Florida. Engineers discovered critical integration flaws during initial trials. Software glitches prevented proper weapon release. Mechanical stress threatened aircraft structural integrity. 24 months of modification solved every problem. The smart fuse is the game changer, the hidden brain inside the bomb. It's not just a timer or a trigger. It's an advanced system that thinks in real time. As the weapon slams into the earth, the smart fuse begins to work instantly. Tiny sensors activate, reading everything around them. It scans the ground layer by layer, measures how thick the concrete is, detects how deep the steel reinforcements go, maps out underground chambers, tunnels, and vaults that might be hiding something important. It studies the resistance of each layer, calculating the best place to unleash its power. Instead of exploding on impact like older bombs, this one waits. It punches through soil, stone, and reinforced concrete with incredible force, digging its way deep into enemy territory. Only when the sensors confirm it's reached the heart of the target, where it will do the most damage, does the fuse allow the bomb to detonate. That delay isn't hesitation, it's precision. It ensures the explosion doesn't waste its power on surface walls or shallow bunkers. Instead, the smart fuse delivers destruction exactly where it's needed, deep underground, where the most protected assets live. It's a level of control and intelligence that transforms a simple bomb into a surgical weapon. One that doesn't guess, it knows. And when it finally goes off, the result is total collapse, leaving no place safe, not even beneath miles of Earth. Now, 7 Bravo 2 Spirit bombers carry 14 of these weapons toward Iranian nuclear facilities. Each pilot trains for this moment throughout their entire career. The aircraft approaches Iranian airspace at 35,000 feet altitude, cruising at 450 knots airspeed. Ground-based radar systems sweep the night sky, searching for incoming threats. The stealth bombers remain completely invisible. Their composite skin absorbs electromagnetic energy like a sponge soaking water. Heat signature stays cooler than surrounding air temperature. Target acquisition begins 50 miles from Fordo facility. Onboard computers calculate wind speed, air density, and gravitational pull. GPS coordinates lock onto underground enrichment centrifuges with surgical precision. Bomb bay doors crack open against screaming wind. The lead pilot's finger hovers over the release button. 20 years of engineering, billions of dollars in development costs, thousands of hours testing and retesting. Everything depends on the next 3 seconds. Weapon release authorized. 2 massive shapes tumble through darkness toward Earth below. Their guidance fins adjust trajectory mid-flight, correcting for crosswinds and atmospheric pressure. Impact occurs exactly where engineers predicted 20 years ago. The underground explosion registers on seismic equipment across 3 countries. But something goes wrong with the 7th bomber. Warning lights flash red across the cockpit dashboard. Engine temperature spikes beyond safe limits. Fuel leak detected in the left wing tank. The pilot faces an impossible choice: abort the mission or risk everything for one final strike. The damaged bomber limps toward home, but Iranian radar operators just detected something that changes the entire strategic equation. 0315 hours, Tehran time. Iranian Air Defense Command stares at radar screens showing impossible readings. 67 aircraft signatures appear simultaneously across their airspace. Ghost contacts multiply every 30 seconds. Electronic warfare systems scream warnings throughout the command bunker. None of these contacts represent real aircraft. Operation Midnight Hammer begins with the greatest deception campaign in modern warfare. American planners spent 18 months crafting this elaborate shell game. Electronic warfare aircraft launched from 3 different carriers, broadcasting false radar signatures across Iranian detection networks. Each decoy transmitter mimics the radar cross-section of heavy bombers approaching from multiple directions. The real Bravo 2 Spirit bombers remain completely invisible. Ramstein Air Base, Germany. 2 hours earlier, the EC-130 Compass Call aircraft departed for the Eastern Mediterranean. These electronic warfare platforms carry advanced jamming equipment designed to blind enemy radar systems. Call sign Wizard. Flight begins broadcasting interference patterns across 17 different radar frequencies simultaneously. Iranian operators watch their screens dissolve into static. Meanwhile, decoy operations unfold across the Pacific Theater. 3 Bravo 2 Spirit bombers departed Andersen Air Force Base, Guam, flying westward toward Japan. Amateur aircraft spotters photograph the distinctive triangular silhouettes. Social media posts spread across the internet within minutes. Defense journalists track the flight path, reporting imminent strikes against North Korean facilities. The real strike package flies eastward from Missouri, maintaining complete radio silence. Advanced drone swarms launch from concealed positions throughout the Persian Gulf. 48 unmanned aerial vehicles stream toward Iranian coastlines, each broadcasting electronic signatures identical to cruise missiles. Iranian surface-to-air missile batteries activate, tracking dozens of incoming threats that exist only as electronic ghosts. Real Tomahawk cruise missiles approach from the opposite direction, skimming wavetops below radar coverage. Inside Tehran's Integrated Air Defense Center, chaos replaces calm efficiency. Radar operators report conflicting data streams. One screen shows massive bomber formations approaching from the northwest. Another displays cruise missile swarms attacking from the southeast. A third monitor tracks fighter aircraft penetrating from Syrian airspace. All contacts vanish simultaneously at 0205 hours. The electromagnetic spectrum clears like morning fog lifting from mountain peaks. Iranian radar systems reset to normal operating parameters. Operators breathe collective sighs of relief, believing they survived a sophisticated electronic warfare exercise. 7 actual bombers continue their approach, now just 15 minutes from weapon release. American cyber warfare specialists infiltrate Iranian communication networks at the exact moment radar systems reset. Malicious code spreads through military data links, creating 30-second delays in target tracking software. Iranian missile batteries receive false coordinates. Fighter aircraft get vectored toward empty airspace. The digital battlefield becomes as important as physical terrain, but Iranian intelligence anticipated American deception tactics. Hidden radar installations throughout the mountains activate backup tracking systems immune to electronic jamming. These hardened facilities detect something approaching from an unexpected vector. 7 faint signatures moving at exactly 450 knots, altitude 35,000 feet. The trap springs shut around America's most advanced stealth bombers just as weapons release begins. The hidden radar stations lock onto America's ghost bombers. But what happens next rewrites every rule of modern warfare. 0208 hours, Tehran time. 7 Bravo 2 Spirit bombers release their weapons simultaneously across 3 separate target zones. 14 GBU-57 penetrators tumble toward Earth in perfect synchronization. This moment marks the largest stealth bomber strike in United States military history. The numbers tell an incredible story. 125 aircraft participate in Operation Midnight Hammer. 7 Bravo 2 bombers carry the primary strike package. 24 Foxtrot, 22 Raptor fighters provide escort coverage. 16 Foxtrot, 15 Strike Eagles sweep Iranian airspace for hostile interceptors. 47 KC-135 Stratotankers deliver fuel across 3 separate aerial refueling tracks. The mission spans 4 continents and requires 36 hours from takeoff to landing. Each Bravo 2 bomber consumes 180,000 pounds of fuel during the round trip. Aerial refueling operations occur every 4 hours throughout the flight. Tanker aircraft rendezvous with the strike package over 12 different coordinates across international airspace. Not a single refueling operation appears on enemy radar screens. Advanced artificial intelligence systems coordinate the entire strike package in real time. Quantum encrypted data links connect every aircraft to satellite networks orbiting 200 miles above Earth. Each pilot receives targeting updates, weather forecasts, and threat assessments every 30 seconds throughout the mission. This represents the first combat deployment of fully integrated artificial intelligence battle management. Unmanned loyal wingman aircraft accompany the manned fighters for the first time in combat operations. 8 XQ-58 Valkyrie drones fly alongside the Raptor escorts, providing additional sensor coverage and electronic warfare capabilities. Each drone carries advanced radar jamming equipment designed to blind Iranian surface-to-air missile batteries. The technology merger creates unprecedented battlefield awareness. Deep beneath Cheyenne Mountain, Colorado, Space Force operators track every moving object above Iranian airspace. Satellite constellations provide real-time imagery of the strike zones with resolution clear enough to identify individual vehicles. Hyperspectral sensors detect heat signatures from underground facilities moments after weapon impact. Iranian Air Defense Command launches their most advanced interceptor aircraft. 4 Sukhoi 35 superflankers scramble from Mehrabad Air Base near Tehran. These fighters carry long-range air-to-air missiles designed specifically to engage stealth aircraft. Their pilots represent Iran's most experienced combat aviators. The interceptors climb toward 35,000 feet, racing to engage the American bombers. But something unprecedented happens during the intercept attempt. American electronic warfare systems activate classified countermeasures never before used in combat. Iranian fighter radar systems display false target information. Missile guidance computers receive corrupted data streams. Pilot communication networks suffer complete blackouts. The superflankers fire missiles at empty airspace while the real bombers continue their weapon runs unopposed. Ground-based battle damage assessment begins immediately after weapon impact. Infrared satellites detect massive underground explosions at all 3 nuclear facilities. Seismic sensors register earth tremors equivalent to magnitude 4.7 earthquakes. Radiation monitoring equipment confirms no radioactive material escapes the destroyed facilities. Mission success exceeds all planning estimates. But as the strike package begins its journey home, Iranian cyber warfare specialists launch their own unprecedented counterstrike against American satellite networks orbiting high above the battlefield. Iranian cyber attacks cripple 3 American satellites within minutes, but Tehran's next move threatens to ignite World War III. 0730 hours, Monday morning. Al Udeid Air Base, Qatar, erupts in thunderous explosions. 18 Iranian ballistic missiles streak across the Persian Gulf at hypersonic speed. Short-range Fateh 310 missiles slam into aircraft hangars. Medium-range Sajal-2 warheads crater runway surfaces. Base sirens scream across the installation as personnel scramble for hardened shelters. 0 American casualties reported. The Iranian counterattack represents the most direct assault on United States military facilities since Pearl Harbor. Base commanders activate emergency protocols developed over decades of Middle Eastern deployments. Aircraft launch from undamaged sections of runway within 45 minutes. Patriot missile batteries swivel toward incoming threats. Medical teams establish casualty collection points despite no reported injuries. Tehran television broadcasts claim total destruction of American air power in the region. Meanwhile, diplomatic phone lines burn between world capitals. The British Prime Minister contacts President Trump at 08:15 hours Eastern Standard Time. French President Emmanuel Macron demands immediate United Nations Security Council session. The German Chancellor calls for emergency NATO Article 4 consultations. Russian Federation President Vladimir Putin orders strategic rocket forces to heightened alert status. Global financial markets collapse within 2 hours of the missile strikes. Dow Jones Industrial Average plunges 800 points during pre-market trading. European stock exchanges suspend operations after catastrophic losses. Oil prices spike to $140 per barrel. Gold futures reach historic highs as investors flee to safe haven assets. Cryptocurrency markets experience unprecedented volatility. The world economy teeters on the edge of complete meltdown. Aircraft carriers USS Gerald Ford and USS Dwight Eisenhower receive emergency deployment orders. Both strike groups race toward the Persian Gulf at maximum speed. Destroyer escorts activate advanced radar systems. Submarine wolf packs take positions throughout the Strait of Hormuz. Marine expeditionary forces prepare for amphibious operations. Iran mobilizes its entire military for total war. Revolutionary Guard Corps commanders issue stand orders across all combat units. Ballistic missile battalions disperse to hardened launch sites throughout mountainous terrain. Fast attack crafts swarm from naval bases along the Persian Gulf coastline. Hezbollah fighters in Lebanon receive advanced anti-aircraft missiles. Syrian air defenses activate Russian-supplied S-400 systems. The Middle East becomes a powder keg waiting for a single spark. Secret diplomatic channels activate between Washington and Tehran through Swiss intermediaries. Back-channel communications flow through encrypted networks monitored by intelligence agencies worldwide. Negotiators work frantically to prevent regional conflict from escalating into global warfare. Time limits compress as military commanders on both sides prepare for expanded operations. Nuclear weapons storage facilities across multiple countries increase security protocols to maximum levels. But intercepted Iranian communications reveal something far more dangerous than regional warfare. Intelligence analysts decode references to sleeper cells activated across American cities. Domestic terrorist attacks planned for major population centers. Chemical weapons smuggled through southern border crossings. Biological agents prepared for release in subway systems. The strike on Iranian nuclear facilities just triggered a completely different kind of war, one that brings the battlefield directly to American soil. China is changing the battlefield with hypersonic missiles that travel over 5 times the speed of sound. Fast enough to hit a target in minutes, even seconds. This marks a chilling shift in the long-standing rivalry with the United States, pushing both nations into a new era of military tension. These next-gen weapons can dodge current defenses, raising a serious alarm around the world. But how deadly are they really? And is the United States ready or already falling behind in this deadly race? Join us as we explore the features and capabilities of China's new hypersonic weapon that can obliterate New York in just 60 minutes. Hypersonic technology is changing the future of warfare faster than anyone ever anticipated, and China is ahead in these advancements. Imagine missiles flying at speeds more than 5 times the speed of sound. That's what hypersonic glide vehicles, or HGVs, can do. But they are not just perceived as formidable due to their exceptional speed. Not only do they fly in an unpredictable pattern, they're designed to zoom through the skies at breakneck speeds while weaving and dodging obstacles. making them incredibly hard to detect or stop with today's defense systems. This makes them very different from standard missiles, which are far more common and have been used in wars for decades. Unlike hypersonic weapons, traditional missiles fly along a set path, making them easier to track and stop with existing defense systems. But how do hypersonic missiles reach their target without being stopped by obstacles and defense systems? This weapon's maneuverability is made possible by the vehicle's advanced aerodynamic design. Hypersonic glide vehicles use high lift-to-drag ratios that give them the ability to glide smoothly through the atmosphere while executing sharp turns and changes in course. The combination of speed and agility essentially turns these missiles into ghost-like weapons that can slip through defenses and avoid detection until it's too late. The technology behind HGVs is a significant leap forward in missile design. Unlike traditional ballistic missiles that travel outside the atmosphere in a predictable arc, hypersonic glide vehicles stay inside the atmosphere for most of their flight, which helps them avoid early detection by radar. Their propulsion and design let them cover large distances with pinpoint accuracy while constantly changing their flight path. This makes them especially effective at bypassing the missile defense shields many countries rely on for protection. Because of these advantages, HGVs are becoming key assets in modern military strategies. Their speed and unpredictability mean that the time for leaders and military commanders to detect and respond to an attack shrinks dramatically from hours or even days down to just minutes. This compressed reaction window makes it much harder to mount an effective defense or to plan a counterattack. The latest breakthroughs, especially by Chinese scientists, have pushed these missiles to new limits. Several reports have revealed that these hypersonic weapons can reach speeds of up to 13,000 miles per hour. At that speed, they could strike targets anywhere on Earth in just half an hour. This kind of rapid strike capability is like having a weapon that can hit from one side of the planet to the other almost instantly, a game changer in global security. This incredible speed isn't just theory. It's now backed by recent research. A report published in the respected Chinese journal Acta Aeronautica et Astronautica Sinica provides fresh insights into the true capabilities of China's hypersonic re-entry glide missiles. These missiles can reach speeds of up to Mach 20, about 21,000 kilometers per hour, or around 13,000 miles per hour. That's more than 25 times faster than a passenger jet. At such speeds, they can fly high in the atmosphere and hit targets across the globe in record time. Even more shocking is the study's claim that specific hypersonic missile variants can be fired from satellites or space-based platforms. If true, this means they could descend from orbit and strike with almost no warning, giving enemy defenses just seconds to respond. According to the Chinese researchers, this kind of attack would drastically compress the adversary's early warning system response time, making it far more challenging to defend against and increasing the chances of a successful hit. Adding to the complexity, researchers from China's People's Liberation Army Rocket Force have highlighted the ability of these vehicles to perform sudden, large leaps or swings during their flight, which adds to their evasiveness. This maneuverability is made possible by their special aerodynamic design that maximizes lift while reducing drag, allowing the glide vehicles to move quickly and unpredictably through the atmosphere. This study supports a controversial report from 2021. At the time, the Financial Times quoted the United States military intelligence, stating that China had tested 2 hypersonic weapons launched from near-Earth orbit. That news sparked global concern, but some military experts dismissed the idea of space-launched missiles as science fiction. Now, China's military scientists seem to be confirming that such technology not only exists, but may be further along than many thought. China has already shown off its hypersonic firepower to the world. One example is the DF-17, a sleek and maneuverable missile that made headlines when it was paraded through the streets of Beijing in 2019 to celebrate the 70th anniversary of Communist China. The DF-17 is believed to carry a hypersonic glide vehicle that can change direction mid-flight, making it extremely hard to track and nearly impossible to intercept with today's missile defense systems. One fascinating aspect of these re-entry glide vehicles is their flexibility in deployment. According to the study, RGVs can be launched not only from ground-based platforms, but also from satellites or other diverse platforms. This flexibility adds another layer of strategic complexity, as these weapons could theoretically be launched from space, further complicating detection and defense. The strategic impact of HGVs is huge. Because they can bypass most missile defense systems, they change the balance of power in military conflicts. Countries with this technology can strike faster and more accurately, while their enemies struggle to protect themselves. This new threat forces nations to rethink their defense strategies and develop new technologies to keep up. China's research into this field shows just how serious it is about building the most advanced weapons on Earth, and possibly in space. If this technology is successfully deployed, it could shift the balance of power in future conflicts and compel other nations, particularly the United States, to accelerate their own hypersonic and space defense programs. In a resurfaced interview from November, United States Secretary of Defense Pete Hegseth warned about the scale of this threat. He said that in the event of a war, China's hypersonic missiles could take out 10 aircraft carriers in the first 20 minutes of the conflict. That's a chilling thought, considering how important aircraft carriers are to American military power. Take the USS Gerald R. Ford, for example, the United States Navy's most powerful aircraft carrier. When it set sail for its first deployment in October 2022, many experts raised eyebrows. With a towering structure rising 9 stories above the waterline and a 5-acre flight deck, it became the largest and most expensive warship ever built. Costing $13.3 billion, it was designed to carry 4 whole squadrons of fighter jets and serve as a potent symbol of American naval strength. However, despite its impressive features, some analysts have warned that it might already be outdated, especially in light of rapidly advancing Chinese hypersonic missile technology. According to a United States Department of Defense report published in December 2024, Beijing now possesses the world's leading hypersonic missile arsenal. That's a serious concern for the United States military, especially when a single hit from a high-speed missile could destroy even a massive vessel like the Ford. These hypersonic weapons, traveling at speeds above Mach 5, are difficult to track, even harder to intercept, and designed to exploit the vulnerabilities of slow-reacting defenses. Experts believe such an invasion could occur by 2027, and if hypersonic missiles are used, United States naval dominance could be seriously compromised. According to the United States Secretary of Defense Pete Hegseth, China is investing billions into building an army that are specifically designed to destroy the United States. But the United States has responded to these developments. To counter this looming threat, the Pentagon has been working to develop laser weapons that can neutralize hypersonic missiles. Since the USS Ford was built to support advanced technologies, there is hope that one day it will carry powerful laser systems. These lasers, unlike conventional missiles, can fire at the speed of light. That gives them a better chance of hitting fast, maneuverable missiles like China's DF-17 before they reach their targets. Laser weapons come with another major advantage. They don't run out of ammunition. As long as the ship has power, the laser can keep firing. From a cost perspective, laser weapons also make sense. According to the Congressional Research Service, each shot from a high-powered laser could cost just $1 to $10, while a single defensive missile might cost up to $10 million. Despite this promise, the United States is still years away from deploying reliable, high-powered laser weapons capable of defending against hypersonic threats. In 2014, the United States Navy tested its first ship-based laser weapon, the 33-kilowatt ANSEQ-3 laser weapon system, also known as LAWS, on the USS Ponce. During the test, the laser silently targeted and destroyed a mock speedboat and even shot down a drone. But due to performance and operational limitations, LAWS never moved beyond testing into full production. 5 years after testing its first laser weapon, the United States Navy tried a stronger one, 5 times more powerful than the original LAWS. In 2019, it installed a 150-kilowatt laser weapon system demonstrator on the USS Portland, an amphibious transport ship. During sea trials, the laser hit a stationary test target successfully. However, by 2023, the system was removed from the ship, and the Navy stopped funding the program, showing the slow and uncertain pace of laser weapon development. Then came a more permanent step. In August 2022, the Navy mounted its first fully integrated laser weapon on a warship, The Arleigh Burke-class destroyer Preble. The system, named Helios, is a 60-kilowatt laser connected to the ship's Aegis radar and weapons control system. Developed by Lockheed Martin, Helios can blind sensors, destroy drones, and possibly small boats. Lockheed believes the system might be upgraded to 150 kilowatts in the future. A weapons test in 2024 confirmed Helios zapped an aerial drone, although the full details of the test haven't been disclosed. However, taking down hypersonic missiles would require a much stronger laser, one with at least 300 kilowatts of power. This growing urgency is not just about who has the fastest missile. It is about how the entire nature of defense must change. If one country gains an edge by having missiles that can strike faster and more precisely than anyone else, it could change how wars are fought and deter enemies in entirely new ways. But it also raises the stakes, pushing other nations to catch up quickly or risk falling behind in defense. This fast-paced development is stirring up tension worldwide. Countries are investing billions into research, not only to build these hypersonic weapons, but also to create systems that can defend against them. The challenge is enormous, and no one has yet found a perfect solution to stop these lightning-fast missiles. But while the global race heats up, it's not without its hurdles, especially for China. Led by Professor Guo Yang, researchers at the PLA Rocket Force have pointed out critical challenges in China's hypersonic glide vehicle systems. One key issue is the system's strong infrared signatures, which could make the vehicles easier to detect from long distances. This visibility potentially reduces the element of surprise and gives opponents more time to respond. Another limitation noted in the study is the relatively low overload resistance of the vehicles. This restricts their maneuverability during critical terminal phases of flight, meaning they may not be able to make as sharp or sudden moves as needed to avoid interception. Additionally, communication bandwidth limitations during these phases could weaken the vehicle's operational power, making it harder to control precisely in the final moments before impact. The study also discusses re-entry glide vehicles, a type of hypersonic weapon that combines aerodynamic design with high-speed maneuverability. These vehicles utilize a high lift-to-drag ratio, which allows them to glide through near space, enduring overloads of 3 to 5 times the force of gravity. This capability enables them to make large leaps or swings within short time frames, allowing for unpredictable flight paths that are difficult for missile defense systems to track or counter. HGVs operate at speeds of Mach 5 or higher, with some reportedly reaching Mach 15 to 20. At these speeds, the vehicles can cover vast distances extremely quickly, potentially striking global targets within 30 minutes. This dramatically compresses an adversary's response and deployment window, making it much more challenging for them to mount a timely defense. In related news, hypersonic propulsion technology is also advancing rapidly outside China. Last month, scientists from the United States and the United Kingdom completed a major test of a hypersonic propulsion engine designed to power a next-generation hypersonic cruise missile. The test involved 233 runs at various hypersonic speeds, marking a critical milestone in hypersonic weapon development. This engine makes use of air-breathing technology, which allows it to travel farther than conventional rocket engines by using oxygen from the atmosphere instead of carrying its oxidizer. Hypersonic glide vehicles force a rethink of many established military strategies. Missile defense systems built to stop slower, less agile ballistic missiles may struggle against these new threats. To keep up, countries will need to develop faster tracking technologies, more advanced interceptors, and new tactics designed specifically for hypersonic threats. The battle to control and defend against hypersonic technology is rapidly reshaping the future of warfare, with global security hanging in the balance. This propulsion breakthrough is part of the UK's Ministry of Defence Team Hypersonics program, aiming to deliver a hypersonic weapon technology demonstrator by 2030. The goal is to give the UK Armed Forces and their Western allies a significant operational advantage in future conflicts through this transformational technology. The successful tests validated the engine's robustness and performance across the full range of supersonic to hypersonic flight speeds. This achievement not only advances the UK's hypersonic capabilities, but also lays the groundwork for future improvements and upgrades to the technology. With the ongoing advancements in hypersonic propulsion and weapon design, the future battlefield will look very different. The rapid evolution of these technologies promises both new opportunities and complex challenges for national defense in the coming decades. All three branches of the United States military are racing to also build hypersonic weapons. The United States Army and Navy are teaming up on a shared glide body design, which will power both the Army's land-based Dark Eagle missile and the Navy's ship-launched conventional prompt strike system. Although the program has hit several delays, the Army recently suggested it might deploy these ground-launched missiles by the end of fiscal year 2025. A key test is expected in December. Meanwhile, the United States Air Force has faced more challenges. It was working on two hypersonic programs, the ARRW, or Air-Launched Rapid Response Weapon, and the Hypersonic Attack Cruise Missile. While the ARRW was officially canceled, a surprise test was carried out from Guam, and the program even received extra funding. However, the Air Force is now focusing its efforts on the HACM. On the other hand, the UK's hypersonic weapons program is still essentially a mystery, with few confirmed details available. Experts believe the new missile might be launched from warships, fighter jets, or ground platforms. It could possibly be used with the Royal Air Force's F-35B fighter jets, or even with the advanced sixth-generation aircraft that the UK is building alongside Japan and Italy. Interestingly, the entire program is being run directly from the Ministry of Defense headquarters in Whitehall, rather than by one of the traditional military branches. Hypersonic weapons travel much faster than standard cruise missiles. If the UK successfully develops them, it could break through modern air defenses and boost its military strength, especially important given the rising threat from Russia and less focus on Europe's security from the United States. President Donald Trump's unpredictable decisions and distant stance toward European allies have pushed many countries, including the UK, to become more self-reliant and invest in new defense technologies. This growing interest led Prime Minister Keir Starmer to pledge the largest boost in UK defense spending since the Cold War. This includes funding for futuristic weapons such as hypersonics, directed energy systems, and advanced air defense. In fact, since late 2023, the MOD has been working with around 80 companies under the Hypersonic Technologies and Capability Development Framework Agreement, treating hypersonic development as a national mission. Other countries are not far behind. India tested a long-range hypersonic missile in November 2024, capable of carrying multiple payloads over 1,500 kilometers. In January 2025, it successfully tested a new scramjet engine on the ground. France is working on the ASN-4G, a nuclear-capable hypersonic missile that will be launched from Rafale F-5 fighter jets. Even heavily sanctioned countries like Iran and North Korea are developing hypersonic weapons. Iran unveiled the Fatah missile in June 2023 and claimed to have used it in an attack on Israel in October 2024. North Korea test-fired its Hwasong-16B glide vehicle, and in January 2025, launched another missile reportedly flying 12 times the speed of sound, over 1,500 kilometers. With all these advancements worldwide, the United Kingdom is pushing hard to join the elite club of hypersonic nations. If successful, Britain will gain a powerful, almost unstoppable weapon to defend itself and support its allies in future conflicts. Thanks for watching. While you are still here, click on the link on your screen to check out another of our videos. See you there.